Alright, hey everyone. So, I'm hoping to get through organic chemistry. We're gonna go through all 12, and I also show you what is going on, but I'm also gonna try to show you exactly how to practice because I will tell you this that if you practice organic chem with just Anki cards, it can get you through a lot of organic chem that involves nomenclature, which is a lot of organic chem. So they can help. Flashcards, whoops. I'm just gonna write that down. Flashcards can help, like Anki, for example. Doing a pre-made Anki deck can be helpful, but for other things, you want to focus more on practice questions. So I haven't been the master of finding all the great resources. Right now, my own website that I made for practice questions works mostly best on biology section. So the biology section it works good in. Behavioral sciences, so psychology, sociology, it's good in. Math, it's great in. Biochem is also like 70% there. In organic chem, I would give it 60% there, trying to make it better for everyone. And general chem is there, it's good. And the reason why it's not as great for right now, artificial intelligence isn't that great at generating all these good images and then doing practice questions on them. So I'm going to try in this video to also show you where to find some practice. Okay, so let's just start with chapter 1. And so chapter 1 is about naming. How do you name a carbon chain or alkanes? How do you name those? So if you have just one of these, one carbon attached to 4, it's known as methane. But if you get two, like that, and then they're attached with H, it turns into ethane, and then it keeps building. So what organic chemistry is all based around, as you'll notice for all the beginners, is C and H. So hydrocarbons, basically. And so carbon and hydrogen. And so if we go to propane, we get 3 of these together with attached to hydrogens going out this way. And then so on and so forth as you move down this table. And that's naming simple alkanes, straight chain alkanes. They even go up to like 30 over here. Yeah. And then you want to understand the IUPAC naming conventions overall. But it's going to be hard to understand how this works if you don't know what the substituents are quite yet. But we'll just go over this first then. So first you're going to find the parent chain, and which is the longest carbon chain that contains the highest priority functional group. And then you're going to number the chain in a way that the highest priority, so what surprises me is that they didn't list highest to lowest priority group, so I'll show an image of that later. Highest to lowest priority. Name the substituents with the prefix, and then assign a number to each substituent depending on the carbon it's bonded to. So let's just go right into practice because again, like I said, organic chemistry is a lot of good practice. So let me get something up for you guys. So I'm going to teach you guys how to find practice questions, and it sounds so odd and dumb, but I know it could be hard for a lot of people to find the practice questions. So just type in IUPAC naming conventions, type in what you're learning, and then you'll see a bunch of forms that are trying to teach you what it is, but not enough practice questions. So where are they? We don't know. So just type in that and then put practice questions with answers. Okay, and then the first link that I already checked out, which is actually good, is Khan Academy. So you can trust Khan Academy. Khan is doing amazing. You can also donate to him, which is cool. Because it does run them a lot to cost for the site. And then you can go ahead and try naming the organic molecules. So I'm going to put this onto the whiteboard so we can work on some together based on the IUPAC naming conventions. Okay, so as you can see, we have this chain here. Now we're going to follow. I'm just going to do one question as one example, and then we'll do another question. So the first step is you're going to find the parent chain. And so the parent chain would be the largest carbon chain. So it's very easy to be like, oh, it's just this one here. But it's not. That's not the longest carbon chain. So each of these will represent C, by the way, like this. And so this is also carbon here. These are all carbon, right? So if we count where the longest chain is, so let's try this one. 1, 2, 3, 4, 5, 6. Okay, that's pretty long, but let's try another one. So potentially it could be like that. This is a chain that's quite long. Or you could try this. This one looks even longer. So then you have 1, 2, 3, 4, 5, 6, 7. That is the longest carbon chain. That is definitely the longest carbon chain. So now we found the longest carbon chain. Now we have to name it. So what you have to do is realize that this is an alkane, right? It's just a single straight chain, and it has 7, right? So we've called it that heptane. And these follow like Greek things. So if it's yeah, these follow Greek things. So I'll show you in a second how that works. But we have 7 here. So this is what we're gonna call heptane. Now step 2 is to number the chain in a way that the highest priority functional group receives the lowest number. So we're going to go find the branches that branch out of this parent chain. So there's one branch here, and then there's another branch here. So what you're going to do is this is how I do it, but you're going to look at based on the number of the parent chain, 3, 4, 5, 6, 7. So this one is on 3. So 3, we have one side chain on 3, and then we have another branching out here, and we would call, and then that would be 5. It's on 5, carbon 5, so I'll write down 5. Now, what you're going to do, so that's not very conventional in trying to show you, but as you can see, we found the parent chain, right, the longest carbon chain, and then we found the substituents. Now, what we're going to do is we're going to look at the question and answers. All right, so as you can see here, these are the following choices that we have. So we already know that we have some sort of alkane. So this is our parent chain. Parent. I'm going to write that down, parent. Right, so these would be our parents. Not literally. And then so we counted 7, and hept stands for 7. Hex would be 6. We didn't find the longest parent chain we found was 7, so we could cross C and D out, right? Now we're gonna name for the rest. So these would be our substituents, right? The side chains, in other words, not the parent chain. The side chains were the substituents. So now we know that this is 1, 2, 3, 4, 5, 6, 7 carbons long. We need to find the side chains. So the side chains is one of these and one of these. So one of these is called methyl, and this is called ethyl. All right, so I don't know if the review sheet will show that part. Whoops, what happened here? Here. So where's methyl? Yeah, so they're following these special prefixes here, where you have meth as a prefix, eth for 2 carbon chain, prop for 3 carbon chain, and instead of 4 is but, pent is 5, and then hex, hept, oct, non, dec, and so on and so forth. It goes all the way up for this chart very far. I would say at least know up to 10 for now, and then as you get better and better, you can know these ones as well. Whoops, let me get out of my thing. Yeah. All right, so now we know that this is methyl because it's 1. One number of carbons is 1, right? And then if we have 2, it's eth, so they call it ethyl, right? So that's why these are here, ethyl and methyl, ethyl and methyl. Now we have to figure out, okay, then what do these numbers mean here? Well, these numbers stand for the location of where that ethyl group is. So we counted 1, 2, 3, 4, 5. The ethyl group is on the 5th carbon, so this one already looks correct. And then 1, 2, 3, this methyl is on 3. So we might be doing something wrong, to be honest, but we got 3. I don't know if it's right or wrong yet. Now we can count by using a different parent chain. So that's one way we could do it. So our parent chain might be wrong. So we'll see how this works now. So we have that. Now let's look for the other one. 1, 2, 3, 4, 5, 6, 7. Okay. So now this looks a little bit different. The methyl's on 5 and the ethyl is now on 3. Now the question is, these are technically both correct. It just depends where we started counting. So should we count one from this side going up this way? Or should we count one from this side going down this way? Should we go this way basically or this way? And the answer has to be, if we go back to our whiteboard, based on here, highest to lowest priority functional groups. Highest to lowest priority. And that's how you know. So let's go to find a thing of that. Highest to lowest priority. So here you can see highest to low. Oh, that doesn't look that very good. That one's not that good. This one, highest to lowest priority functional groups. Now both of ours had alkanes. Where are they? Alkenes. No, not that one. Or the alkanes. Anyway, why are they not listed here? Give me one sec. Here we go. Google listed it out really well. So just type in highest priority and they'll give you a list. So as you can see, we go from carboxylic acids all the way to alkanes. And we only have alkanes. So that means, you know, it's still going to be hard for us to determine which one. But I'm going to explain why in a second. So with my logic, I would deduce as a student to choose 3 ethyl, 5 methyl. And we're going to check if that's correct. Check. There you go. And it was correct. So you see a step-by-step solution. That's our economy is pretty good. And then this labeling ensures that the longest continuous carbon chain is selected as a parent. So we did that. And if the two options result in the same locants for substituents ethyl and methyl, remember we found those ones, the numbering follows alphabetical priority, where we assign the lower number to the substituent that comes first alphabetically. So it has to do not with the functional groups, because these are both alkanes, right? It has to do with the alphabetical priority. But if there were different functional groups and it was more complex, then you would have to do it listing out the based on priority, and then you could do like alphabetic, right? All right. I hope that kind of helped, but you can always find more practice online. Okay. All right, so now we passed this one. Okay, so now we can go into hydrocarbons and alcohols. So hydrocarbons we saw is just C and H. A lot of organic chemistry is just C and H. As you can see, C and there's an H there. This is N, and sometimes N too. Sometimes N, and then C and whatever else, and oxygen too. And then C, and you notice C's carbons are never really gone from organic chemistry. But you'll notice that it's mostly C, O, N, stuff like that. So anyway, those are hydrocarbons. So now, and then now we're going to look at alcohols in this topic here. So alkanes, remember, I showed you alkanes earlier, which is great, are hydrocarbons with no double or triple bonds. So let me see if I can find pictures. I'm kind of upset that my laptop screen is kind of small, so it's hard to show everything. But we can do fine. We can do fine. So here's an example of the methane and then ethane, right? And they also give you the formula to find alkane formula, which you can use here. It's over here as well. And so naming alkanes are according to the number of carbons presented plus ane, right? So methane, right? Meth is the prefix for 1. So you put methane and you get methane. And then you can keep going from there. There's other examples here. Okay. Now we can go over the alkene. And the alkene is a double bond. So basic alkene looks like this. The alkane looks like that. But the alkene looks like this, triple bond. So the single bond is your alkane, which is right here. The double bond is your alkene, which is right here, and the alkyne is this one, right? And so the alcohol, let's say you have a carbon chain drawn like this. So this is all technically C, but they don't draw it there, by the way, right? So let's say we have one line like that. And now let's say I have an OH group right here. That's an alcohol. Alcohol is this OH. And how do we name it? We use the suffix ol. All right, let's give an example. Here's an example of ethanol. So the reason why it looks like the hydrocarbon, like an alkane, and it has 2. You're like, oh, why don't we just name it 2 plus a side branch? No, because why? Alcohols have higher priority than double or triple bonds. So alcohols are higher priority. So we're going to name the main thing ol with the suffix ol, as it says here. Okay, a diol contains 2 hydroxyl groups. So let's go find a diol as an example. This is why you need practice questions too. So here we have a 1,2 diol. So they would name where the diol is, which carbon it's on, and then they would put diol. And so a geminal diol is different from a vicinal diol versus vicinal diol. So this is a good example of when the 2 hydroxyl groups, the OH is called hydroxyl, the 2 hydroxyl groups are on the same carbon. So this would be geminal. Oh, here's a good picture, I think. Nope, it doesn't show vicinal. Where's vicinal? Let me go find a picture of that somewhere. Here, vicinal is here, 2 adjacent. So you see this carbon, they're beside each other, and the hydroxyl groups are adjacent to each other, but they're not on the same carbon. Okay, so it'll kind of look like that, whereas the other one looked like that almost. Okay, that's enough for that one. So this is the basics that you want to start with, and you want to know how to name them. So stop the video, go practice, get your practice in a little bit, practice naming alkanes and alkanes with alcohols, and technically those alkanes with alcohols will be alcohols, and you would have to name alcohols. Anyway, now we can go on to other functional groups. So what we're learning, just as an overview for someone who doesn't understand the chemistry, is you need to know the functional groups and their priorities, like I showed you earlier. So here are the functional groups, and what we're doing is we're trying to learn each of them, because organic chemistry is knowing what these functional groups are, first of all. So we're going to go over carboxylic acid next, which is over here. So carboxylic acid and their derivatives. So carboxylic acid looks like this. So you notice a C, double bond O, and then whatever, R can be like whatever on the side, basically. It's like fill in the blank. Like remember in biochemistry, we were learning about amino acids and their R group, amino acids within R group. The R group is like fill in the blank, whatever could be there, you know. And so the main thing about carboxylic acid is it looks like that. And the highest priority functional group is the highest priority because it contains 3 bonds to oxygen. So really what you have to take from that is its highest priority. And you have to memorize the functional groups priority list. Where was our priority list by Google? Here it is. Is this correct? Yeah, so highest priority. They added some extra stuff here that you don't necessarily have to know all of those, but yeah, highest priority to lowest priority. Now we can get into, and you name it with oic acid. So carboxylic acid. So these are common names. Sometimes you have to know the common name up to like 3 carbons. So formic acid, acetic acid, and propanoic acid. They differ in how many carbons they have. So formic has 1 carbon, acetic acid has 2, and then propanoic acid has 3. But those are the common names. So how you name it with a, let's see if this picture is good. You would do, no, this one's too much. Here we go. This is a good picture. So methanoic acid, then ethanoic for 2, propanoic for 3 carbons, butanoic for 4, as you can see them, and pentanoic acid for 5. And then if they're ever drawing it not in the expanded form, it would be like with the OH and just a line like that. Like this is a simplified diagram of what it would look like down here. And so you would use oic acid as the suffix to name carboxylic acids. And you use the same prefixes we would have used up here. The common names are just like other common names that, so methanoic acid is also the common name as formic, right? We just saw those. And learning the common names up to like 3 can help you. Yeah. Okay, so now we can go into esters, which look like this, and amides, which look like this. So amides, you notice, has this N here, amide, and esters have just an O, and then they attach to something else. So by definition, an ester is a carboxylic acid derivative where OH is replaced with OR instead. And then an amide is when you replace the OH of the carboxylic acid with an amino group that may or may not be substituted. So basically, these two, right, can come from a carboxylic acid because they're derived from it. Okay. And then you have to understand their structure, what they look like, memorize that, mostly memory. Aldehydes and ketones. So aldehydes look like this. You can notice the C and then the H here, so it's very simple. A ketone is interesting because you can imagine if we expand this further, there's like other carbons here, here, here. There could be, or it could be simple like that. You have a ketone like this, simple ketone. And so basically, this one looks like a double bond between something, but these were at the end, right? These are at the end of the long chain like this. Would have been a chain, right? And then you would have had carbon at the end here, double bonded O, and then you have a chain here, and then O, and that would have been your ester right there, right? But this one is like in the middle of 2 long chains. Like it could be there, you know? All right. How do I know that? It's because of the R. The R is telling me. I'm not pulling any special knowledge there. All right, carbonyl group is a C bonded to the O. Aldehydes and ketones both have the carbonyl group. So you can see that clearly. Aldehydes, carbonyl group on terminal C. So that's why we were talking about terminal and non-terminal. So I can see the C is at the very end, terminal. So an aldehyde would be like this. Whoops, I put a C there. Like that. And this would be the carbon right here. And so you can see that this is at the end, terminal. That's what I meant. And then the ketone is at a non-terminal carbon. So it would be somewhere in the middle, something like that. You know? All right. That's cool. And then now we can get into, let's see if we have this one. Okay, primary, secondary, and tertiary alcohols and amines. So for alcohols, it looks like this. For primary, and then for secondary, it looks like this. And for tertiary, it looks like this. For amines, you have amines that look like this, primary. For secondary, look like this. As you can see, now there's 2 carbons there. And tertiary, which looks like this. As you can see, there's now 3 carbons there, right? All right. So now that you've gone through aldehydes, ketones, carboxylic acids, and their derivatives, and also primary, secondary, tertiary alcohols and amines, then you want to go and find some practice and do that. All right. And then we have our structural isomers. Structural isomers, so naming variants. So isomers, we're now in chapter 2, and we're naming variants. Naming variants, or different versions of a molecule. So structural isomers share the same molecular formula. So they're the same molecule, right? Same molecule, but they have different physical and chemical properties still. They're going to be arranged, they're going to look different, but what they are composed of is the same thing because they have the same molecular formula. Okay, so let's start first with stereoisomers. So actually I need to show examples of structural isomers because this is really small example, nothing really there. Okay, so basically what you want to know before we head into the chapter on isomers is that isomers can be split into different types of isomers. You can have constitutional isomers, which is just what we looked at, also known as structural. You can also have stereoisomers, which can branch into diastereomers and enantiomers. And diastereomers can have cis or trans isomers, and then this other stuff down here, which is conformers and rotamers. So, whoops, why is it taking me there? So a lot of what I learned, this is actually a good flowchart for anyone learning as well. Just pick a flowchart and go with the flow. But that was just an overview. So what we just went over is just one type of isomer that exists, right? This is not all isomers. These are only for structural isomers. So structural isomers, only that will happen. Okay, so just to give a broader overview before we go into it, because I know it can, the sheet, if you didn't know much about the sheet, it can get confusing. Here's an even simplified flowchart. Flowcharts can help a lot. Okay, next we have stereoisomers. So remember this one. Stereoisomers have different stereoisomers have same connectivity, but they're different in 3D space. And all the flowcharts will show you that same formula and same connectivity, spatial isomers. I'm just looking for a picture that I think best suits meltdown, but we'll just go over it. So stereoisomers are compounds with atoms connected in the same order, so connected in the same way, but they differ in their 3D orientation, as we just saw read out in one of the images on the flowchart earlier. And they have a chiral center where 4 different groups are attached to a central carbon. So say this is my central carbon. Like in amino acids, the central carbon is there, right? So that's your central carbon, and it's attached to other things. Can be attached to other things. Okay, so that's called your chiral center. And then the 2n rule is that n is equal to the number of chiral centers, and the number of stereoisomers is equal to 2 to the power of n. You need to remember this. Conformational isomers. And then you can also have configurational isomers. So remember we saw the flowchart. Alright, why does the flowchart always go out of view? Give me 1 second to find a good flowchart. Alright, this one's a little bit better. So I like this one because it also adds questions and it has the relevant groups that I was looking for. This one is good too. This one's simpler, but this one I like better. Okay, so you have stereoisomers. We're just looking at them. They can be configurational or conformational. So that's what we're looking at now. You can have conformational or configurational underneath stereoisomers. And so, where do I add this? So an anti, as you can see, you look for these carbons look like they're totally opposite from each other, and so it's anti. These carbons are gauche. Look at the carbons. This one is eclipse. They differ by rotation around a single bond. In Gen Chem, sigma stands for single bond. And then cyclohexane, substituents, can be equatorial in the plane of the molecule or axial. So let's go over that real quick. So when people said cyclohexane, it's kind of like a ring, right? Cyclo for the ring. But hexane is for 6 of these. And specifically, cyclohexane can have axial bonds. 6 axial bonds, 1 on each carbon, are parallel, and they go up and down. So axial you can think of goes up and down. Okay. Oh, actually the flowchart's down here. Wow. Meltdown is awesome. Provided you the flowchart. I don't know why I spent so much time looking for it. Yeah, refer to this flowchart. Maybe it's easier to see in light mode, so we might have to do light mode today. But here you go. That's a flowchart. Awesome. Okay, well, that's great to know. So anyway, equatorial. Sorry, this is not equatorial. What are we doing? We're doing everything wrong. Axial is going up and down. All right. Axial is going up and down. Now, equatorial is going kind of side to side. That's how I like to think of it. Or in the plane of the molecule is another way to write it, but it's like side to side in the same, plane, I guess. So if it was that way, it'd be going this way, and this way, and this way. But up and down is a no-no. That would be axial. Axial is up and down, and equatorial is the same plane, right? So it's on the same, it's like side to side almost, like that. And axial would be popping out this way, up and down. All right. You want to think of molecules as 3D shapes as well, by the way, because this is all about having the same atom but connected, but oriented differently in 3D space. Okay, configurational isomers. So we hit, where is it? Over here. So yes, they have interconversion, and that requires breaking bonds. So enantiomers are types of configurational isomers. So where's enantiomers? These are enantiomers. And they're non-superimposable. Both of these are enantiomers of each other. They're non-superimposable mirror images. So if I mirror these two, that's what they are. Opposite stereochemistry at every chiral carbon, and they have the same chemical and physical properties. That's important to note. Except for rotation or plane polarized light. That's also important to note. Optical activity. The ability of a molecule. So what is optical activity? Right? Optical activity is what it's referring to over here about what the rotation of plane polarized light is. This is an optical activity. So it's the ability of a molecule to rotate plane polarized light. So if D minus or plus means it can rotate to the right, L minus or just negative means it can rotate plane polarized light to the left. All right. So depending on the molecule, it will have different optical activity. The racemic mixture is when you have 50-50 mixture of 2 enantiomers, not optically active because the rotations cancel each other out. That's important to note, that rotations can cancel each other out if it's plus and minus. Cancels it out. All right. And then mesocompounds, wow, my highlighter is big, have internal plane of symmetry and will also be optically inactive. That's important because the two sides of the molecule can cancel each other out. So these are also optically inactive. So it's, as you can see, it's really important to know optical activity when we're talking about enantiomers. And for diastereomers, they're stereoisomers that are not mirror images. So if I try to mirror them, it wouldn't work. This should have been flipped over, right? These can flip over. They're mirror images. Mirror images, diastereomers over here. They're still configurational isomers though, but now they are not superimposable mirror images. Cis and trans. So a subtype of diastereomers is cis and trans. So if you want to branch this out even further from diastereomers, you would have, well, not like that. You have cis and trans. And so cis and trans is a subset of diastereomers, and they differ at some but not all chiral centers. They have different chemical and physical properties. Okay, now that you know all of this, you might want to practice drawing out this flow chart a few different times. And then listing out what you know based on over here of the properties. Or do this after we finish relative and absolute configuration. That's fine too. But yeah, you can do that. And so relative and absolute configuration. For relative configuration, it gives the stereochemistry of a compound in comparison to another compound. For example, D and L. So if you remember in biochemistry, we talked about D and L briefly, and then I told you to review organic chemistry because relative and absolute configuration is all organic chemistry stuff. Yeah, so we're hitting relative configuration and absolute. And relative, an example is D and L. So D means being right-handed, right. L means left, right? So absolute configuration gives the stereochemistry of a compound without having to compare to other compounds. So S and R. So I'm going to explain this better. One second, let's do an image. All right, so I want to give more clear definitions of absolute configuration here. Oh, what happened? I can't draw on it. Absolute configuration here and relative configuration. So if I have absolute configuration, it's you can imagine an analogy that it's like your exact GPS coordinates of the molecule. So if the molecule had X, Y, Z, A, some random stuff, and there's your carbon in the middle, this is the exact 3D shape, for example, 3D shape. And you used to find the exact 3D shape using Kohn-Engel pre-log CIP, in other words, CIP. So if you go back, this is what Kohn-Engel priority rules is about. Finding absolute. So then you need to practice questions to get well at this. And then Z and E for alkenes means Z is the same priority on the same side. E is same priority on the opposite side. So remember that Z and E for alkenes. And then R and S for stereocenters. So a stereocenter configuration is determined by putting the lowest priority group in the back and drawing a circle from group 1, 2, and 3. So R means it will go clockwise, and S means it will go counterclockwise. So this other way here. So this is clockwise. Counter is going the other way. So if I drew it, this would be, sorry, what am I doing? Counter. This way versus the other way. Okay. Fisher projection are vertical lines that go to the back of the page. So Fisher projections you'll see a lot when we write out carbohydrates. They're basically like 2D images, but they're trying to show 3D configuration. So when you see horizontal lines, these are coming out of the page. And then vertical lines go back, vertical lines to the back of the page. So these ones to the back of the page. The horizontal lines are coming out of the page, these ones. So this is equal to that. Altering Fisher projection is switching one pair of the substituents and inverts the stereochemistry. Switching two pairs retains stereochemistry. Rotating the entire diagram 90 degrees inverts stereochemistry. Rotating 180 retains stereochemistry. Do practice questions. Find online on Google for all of that as well. Again, I showed before how to find practice questions, but I'm going to reiterate again because they are important. You're going to go into Google, and you're going to type in what you're learning, like this, pre-CIP priority rules. And then you're going to also either, you could do it straight off of the website that you're finding the pressing questions on, and then type in practice questions and look for them. And same for this, and same for this, and same for Fisher projection, and same for altering Fisher projection. Yeah. So I'll put a check mark here for now, and I might go back to it later on just to show some other examples, maybe, if we have time. All right, organic chemistry 3 should be review if you've done general chemistry on bonding already. So all of this should be review. I recommend just going back to my general chemistry video of the chapter on bonding and quantum numbers. All the quantum numbers are listed for you here. So you should be good with this. If you don't know this, you should not be on organic chemistry first. Go back to general chemistry and review quantum numbers and how to do these formulas, and also how to do practice questions with them. Practice questions. And then for hybridization, sp3 means you have 25% S character, 75% P character. You will have a tetrahedral geometry with 109.5 bond angles. This is given to you via Vesper. And Vesper is also in your general chemistry textbook for Kaplan. sp2 is 33% S character, 67% P character, and with a trigonal planar geometry with 120 bond angles. Sp is 50% S character and 50% P character. You have a linear geometry with 180 bond angles. Resonance is when you have a delocalization of electrons in the molecules that have conjugated bonds. Conjugation occurs when a single and multiple bonds alternate, creating a system of unhybridized p orbitals down the backbone of the molecule through which pi electrons can delocalize. So let's go over resonance and conjugation. So here we go. So as we just saw earlier, we saw that conjugation and resonance, as we introduced here, are relevant to each other. So you're going to learn these together, right? And so if I have conjugation, it means there are 3 or more p orbitals lined up in a row. So this may not be the best diagram. Some people might like to look at a more 3D one like this one, and that's fine too. But as you can see, we have p orbitals here that are lined up. So you have 3 or more p orbitals lined up in a row. This is another way that you can show it. And so it's basically like a double bond, then a single bond, then a double bond, right? This is a double bond, and then single, single, double. So then this is not conjugated. It isn't conjugated, as it writes here. So you need a conjugation in order to then have resonance. And resonance means electrons can move or spread across the connected p orbitals. So now the p orbitals are now connected. And that's what they mean by delocalized. So they are no longer localized to this only one p orbital area, right? They're now spread out. In other words, delocalized. So that's what they meant here. Electrons, which pi electrons can delocalize. Okay, for molecular orbitals, bonding orbitals are created by head-to-head or tail-to-tail overlap. So something like that. Atomic orbitals of the same sign. That will decrease. Also, this leads to more stabilization. I think it was written somewhere here. Together, they make molecules more stable. So if you have resonance / the conjugation setup, basically, you have a more stable molecule. I forgot to add that. Note. And so bonding orbitals, yes. So less energy means increases stability. Something you'll notice is that whenever something has less energy, it means it's more stable molecule. But if you have more energy, it means you're less stable. And that's what it says here. And so anti-bonding orbitals have higher energy and they're less stable. So energy and stability are, in other words, what I'm trying to say, inversely related. So single bonds, this should be general chemistry review at this point. Single bonds have 1 sigma and contains 2 electrons. A double bond is sigma and pi, like this, sigma plus pi. Pi bonds are created by sharing electrons between 2 unhybridized p orbitals that align side by side. You want to think orbitals as existing in 3D space, and these orbitals are areas where electrons exist. And triple bonds is 1 sigma and 2 pi. Alright, multiple bonds are less flexible than single bonds because rotation is not permitted in the presence of a pi bond. Pi bonds are not flexible. Multiple bonds are shorter than single bonds, although individual pi are weaker than sigma bonds. So that's important to note. So what it's trying to say here is that if I have a sigma bond alone and I had a pi bond alone, this sigma bond is stronger. That's what it meant here. Individual pi bonds are weaker than sigma bonds. So this pi bond is weaker than this sigma. But if I have a single bond and then I have a double bond and I also have a triple bond. So whoops, this doesn't look very good. Sorry, I'm not the best at this. C. So you have a double bond between these carbons. Oh, I don't have enough space. And then I have a triple bond. So what do you think is stronger? The stronger one is the triple bond, and then it's the double bond, and then the weakest is the single bond. Multiple bonds are less flexible because rotation is not permitted. Multiple bonds are shorter and stronger. So this should be Gen Chem review of basically the strength of bonds, bond strength, and bond length for single, double, and triple. Single, double, and triple. So this should be Gen Chem review, and if you didn't understand this, go back to general chemistry on the quantum numbers and the orbitals. Hybridization is a bit newer though, a little bit. It's more in detail a little bit. Acids and bases now, this is also similar to general chemistry, but it's more towards using organic molecules, obviously, because it's for organic reactions. So acids and bases. So this should be all review for this part. A Lewis acid is electron acceptor, Lewis base is electron donor. It has vacant orbitals or plus polarized atoms. For Lewis acid, Lewis base has a lone pair of electrons, are often anions. Bronze-Lowry acid is a proton donor, whereas Bronze-Lowry base is a proton acceptor. Amphoteric molecules such as something like water, H2O, it can be amphoteric because they can act as either acids and bases. That's why you get autoionization of water. Ionization of water, and it depends on the reaction conditions. Ka is acid dissociation constant, a measure of acidity. So how acidic is that? If you have a high Ka, then you're acidic, really acidic. If you have low, then you're not that acidic, right? pKa is an indicator of acid strength. This is a formula and the trend on the periodic table. they said pK decreases down the periodic table and increases with electronegativity. Alpha carbon is a carbon adjacent to a carbonyl, and an alpha hydrogen is connected to an alpha carbon. Redox reactions are oxidation and reduction reactions. Now you're thinking, okay, why do they have to combine oxidation reactions and reduction reactions together? It's because they occur together. There's no way they can occur separate, right? In these reactions, so because they're occurring together, they just combine them to say redox. Okay. And now the oxidation number is the charge an atom would have if all the bonds were completely ionic. An oxidation raises the oxidation state, assisted by oxidizing agents. You have to know what an oxidizing agent is, and so they write it here. Oxidizing agents accepts electrons and is reduced in the process. So they will be willing to accept an electron and be reduced, so go through reduction. Then what is reduction? Reduction is lowering the oxidation state, assisted by reducing agents. So then what are reducing agents? Reducing agents donate electrons and is oxidized in the process, so it goes through oxidation. Right? Chemoselectivity is when both nucleophile and electrophile in redox reactions tend to act as the highest priority, most oxidized functional group. One can make use of steric hindrance properties to selectively target functional groups that might not primarily react, or to protect functional groups. So before you go into chemoselectivity, you need to understand what the terminology is that they're using. They're using nucleophile and electrophile. So we're going to go through this first. So nucleophile is nucleus loving. So they contain lone pairs or pi bonds, and they have a high electronegativity and often carry a negative charge. Nucleophiles. Amino groups are common organic nucleophiles. Amino. Remember, amino has the N in it, right? Nucleophilicity, a kinetic property in the nucleophile strength. Factors that affect nucleophilicity include charge, EN, steric hindrance, and the solvent. So you need to understand these terms: charge, electronegativity, steric hindrance, and solvent to understand nucleophilicity. Electrophiles are electron-loving. So nucleophiles and electrophiles are different. And electrophiles are electron-loving, so they contain a positive charge. Remember, these nucleophiles are usually, they often carry a negative charge. Well, the electrophiles contain a positive charge, are positively polarized, and more positive compounds are more electrophilic. So they have more, electrophilicity. So you can have a nucleophilicity for nucleophiles and kind of like electrophilicity for electrophiles. So how electrophile are you? A leaving group are molecular fragments that retain their electrons after heterolysis. The best leaving group can stabilize additional charge through resonance or induction. Weak bases make good leaving groups. SN1 and SN2 reactions are really important. SN1 reactions are unimolecular nucleophilic substitution, so 2 steps. And the first step, so what it's doing is it's substituting a nucleophile, and this reaction happens in 2 steps. And the first step is that the leaving group leaves, and they form a carbocation. And the second step is that the nucleophile attacks the planar carbocation from either side, leaving a racemic mixture of products. Remember, we talked about the racemic mixture over here, where we talked about in stereoisomers and isomers. Racemic mixtures are 50-50 mixture of 2 enantiomers. Right, so when you do this reaction, you're getting enantiomers, and so the rate is equal to K times the substrate. And then for SN2 reactions, it's a bimolecular nucleophilic substitution, and there's one concerted step. The nucleophile attacks at the same time that the leaving group leaves. So before it was leaving group leaves, then the nucleophile attacks. This time, it's happening at the same time. Nucleophile attacks while the leaving group leaves, and the nucleophile must perform a backside attack. So it's not attacking from either side. So either side means it can lead to racemic mixture products. But since it's only at the backside, it leads to an inversion of stereochemistry. R and S is also unchanged if the nucleophile and leaving group have the same priority level. SN2 prefers less substituted carbons because steric hindrance inhibits the nucleophile from accessing the actual electrophilic substrate carbon. And this is the rate for that. So I'm going to go over all of that because that was a lot of mumbo jumbo if you don't understand the basics of what an SN1 looks like and SN2 looks like, because a lot of organic chemistry is seeing things in 3D. And then we'll go into some of this other stuff here and what it means too. Alright, so I have a lesson here, and because the subjects need to be, I think that to understand all of this, you need to understand them in a related manner. So we're going to start, before we get into any definitions, we have one thing to hold on to, and it's that almost everything in this unit is a story about electrons changing hands. That's it. Every reaction on this page is really just some atom that has extra electrons meeting some other atom that wants them, and the two of them working out a deal with each other. So that's what reactions generally happen in the first place. That's basically what it is. So I'm not sure if I'm allowed to show all of these pictures from the textbook, but if you look over here, between a Lewis acid and a Lewis base, they form a coordinate covalent bond. And so this is all a story about electrons being accepted and electrons being donated over here. So forget the diagrams for a second, or the complicated looking ones at least. Organic chemistry is basically gossip about who has something that someone else wants. Sometimes it's a full pair of electron up for grabs, and that's for acid and bases, and nucleophiles and electrophiles. And sometimes it's just a couple of electrons quietly changing owners, and that's redox. So it's about who wants what. Okay, so you have those who own electrons. This is acids and bases and who's short on them. And this is the story of acids and bases in redox. It's about status, rich or poor, oxidized or reduced. So who's available to react and how eagerly they are to move. This is the story of nucleophiles, electrophiles, and the SN1 reactions, SN2 reactions that we saw here. Oops. SN1 reactions, SN2 reactions, E1 and E2. So all of these mechanisms, it's about behavior, who approaches and who leaves, and how fast. So parts 1 and 2 are the Wells economy, parts 4 and 7 are the dating economy, and part 3 is about the referee that connects them. So anyways, there's a lot of parts to this whole entire part, but I'm just going to go over the main things. So we already went over Lewis acid and base, but here's a helpful analogy. You can think of a Lewis base as someone standing at a party holding a spare umbrella, and a Lewis acid as someone standing in the rain with their hand out. The base doesn't lose the umbrella forever, and it forms a bond, a shared arrangement, but it's the one supplying it. So that's the base, the Lewis base. Now for Bronze-Lowry acids and bases, it's like this. A proton is like a hot potato with a plus sign on it, or just H+. The acid is desperate to pass it off. The base is willing to catch it. And so the point, it says for your student, but this is a lecture made by the artificial intelligence. Bronze-Lowry is just a Lewis chemistry played with one specific coin, a proton, instead of any general empty orbital. And then I already went through amphoteric, and that's why I already went through water being a classic example, and that it goes through auto-ionization. So we'll move on from there. Ka and pKa, as we discussed, are signs and signals, numeric signs and signals, to determine how acidic something is, how acidic the molecule is. So if we go here, I put it, Ka is your strength of acid in the solution, so how strong is that acid? And if you have a low pKa, then you have a more acidic molecule, and -2 or below means you have a strong acid. And another thing that was incorporated is about the alpha carbon and alpha hydrogen. So the alpha carbon would be, whoops, where do we go? An alpha carbon would be here, this one, and this is the alpha hydrogen. So an acidic H+ ion can easily be lost as well. So anything involving carbonyls, the alpha carbon is a carbon sitting immediately next to the carbonyl group. And so the alpha hydrogen is any hydrogen attached to that alpha carbon, as you see here. And so they matter more in later chapters, but basically what you get from that is that acidic H+ ions can easily be lost. So redox reactions we already went over, which is great. What else do we need? Chemoselectivity. So we have yet to go over chemoselectivity now. Whoops, it's not loading. So basically, in chemoselectivity, both neutrophil, electrophile, and redox reactions tend to act as the highest priority, most oxidized functional group. So chemoselectivity is, think about it this way, who gets selected first? Who gets noticed first, as it writes here, is another way to think of it. So a real molecule usually has several functional groups in it, right? We saw that before when we were doing some nomenclature practice, right, in chapter 1. So we have several other functional groups, and the question is which one will react. And the rule of thumb is that both nucleophile electrophiles tend to hit the highest priority, most oxidized functional group first. So that's what it says here. So analogy is that you can picture a talent scout looking through a crowded room. They don't stop at the first person they see. They stop for whoever's most eye-catching. So functional groups work the same way. The most reactive spot on the molecule gets approached first. Everything else waits its turn. But chemists can rig the room. So that means that chemists can do something called adding protecting groups. Protecting group. Chemists can add a protecting group. And what does a protecting group do? So if you don't want a reaction touching a particular spot, because you know that that spot would probably react, you can park a bulky group there called a protecting group that physically blocks the approach through steric hindrance. So the analogy is that a protecting group is like a bodyguard, and it doesn't change who the most attractive functional group is. That would have been the highest priority, most oxidized functional group. It just stands directly in front of the specific target, so nothing can get close and react with it. So that's the point of what it's trying to say here, is that chemists can add a protecting group so that the functional group that would have been basically chemo selected for first is not, okay, because it's being blocked, essentially. So now we can go on to the nucleophiles and leaving groups. So we already went over nucleophile, nucleophilicity, and electrophiles, which is great. And we also went over leaving groups. Another thing that was actually wrong about up here, it says that pK decreases down the periodic table and increases with En. there's actually, I searched that up on Google, and it says no, pK decreases as En increases. So that's something to note. This probably might be wrong over here about pK, so yeah, be careful with that one. So then going into SN1 and SN2 reactions, there are two ways that can happen, and we already went over those two ways. So just remember that SN1 was those two steps, and SN2 had one step that was basically a merge or a combination of those two steps together. Remember that you get a raised mixture of products for SN1, whereas in SN2 you get stereochemistry that inverts the structure, like an umbrella flipping inside out in the wind. Because think about it, wind attacks the umbrella, right? And then it inverts the structure of that umbrella. So the SN2 reaction is very similar in that way. Okay, awesome. So as you can see from the simplified diagrams here, the leaving group is leaving, and this nucleophile is being substituted into the molecule. This leaving group is leaving, and the nucleophile is being substituted into the molecule. SN1 and SN2. Okay. For E1 and E2, you have elimination. So instead of a new nucleophile bonding to electrophilic carbon, a base reaches over and plucks a hydrogen off a neighboring carbon. The electrons from that CH bond swing into form, and a brand new pi bond, right as the leaving group exits, the two carbons end up double bonded like an alkene. So that's the alkene that we're getting here. Alkene. Alkene is going to be formed now. So remember that in E1, I'm not sure why I didn't really go over E1 and E2 here, which sucks. That sucks. They need to go over E1 and E2. Alright, but for E1, you can, so it's same as SN1, but the leaving group exit on its own, forming a carbocation, and then instead of a nucleophile bonding to that carbon, a base grabs a neighboring hydrogen and the double bond forms. So E1 and SN1 are direct competitors, same starting conditions, same carbocation intermediate, but a different ending. So this ending, obviously we said this before, is alkene. Okay, and now we can go into E2. So you have one concerted step, similar to SN2. You have a strong base, which removes the neighboring hydrogen at the exact same instant the leaving group departs. No carbocation ever forms, and this requires a strong base. E2 requires a strong base and specific geometry between the departing groups. So a good analogy is, think of E1 as the relationship is ending, and the leaving group departs, carbocation forms, and only afterward does the base, which is a friend, convince a nearby hydrogen to also walk away, and the two remaining carbons throw their arms up together. A double bond, a clean break rather than a rebound. Okay, so that's just a very random example, analogy of real life, but basically you have that leaving group, right, that leaves, but then the carbocation forms, and then you have the base that convinces the hydrogen to leave, and then you get carbons that need something, and so what they'll end up having is a double bond. All right, and that's for E1. And then for E2, the base and the leaving group act together, or in the same beat, it says here, like two dancers stepping apart from the center point at once. It doesn't need a carbocation to exist for even a moment. So E1, you notice, needs that carbocation to exist, but E2 doesn't, right? Which is exactly why E2 can happen on substrates that couldn't hold a stable carbocation. So E2 can work with substrates that don't even need that carbocation, because E2 doesn't even need carbocation to go through E2. So elimination winning over substitution isn't only about how crowded the reacting carbon is, it's also about how bulky the base itself is. So a strong bulky base, like a base wearing an oversized backpack, often can't squeeze into a tight backside angle SN2 needs. Remember that SN2 requires, it ends up with inverted stereochemistry because of a nucleophile performing a backside attack. So even on an otherwise open primary carbon. So instead of attacking the carbon, it settles for grabbing a much more exposed hydrogen off to the side. And that's why a strong bulky base pushes even primary substrates toward E2. So solvents. Solvents are what you react with your solute. So if you don't know the general terminology, you need to go back to general chemistry, and learn about solute plus solvent. And you want to go to the chapter on solutions. For review if you're unaware, but this is even in more detail. So a solvent isn't just a fluid. It acts actively and helps or hinders each mechanism by how it interacts with the charged species. So it's not just, so when you mix a solute with a solvent, it's not just a solute that's doing work, it's solvent, it's both of them. So let's see what's happening here. So when you get a polar protic, does it have OH, NH? Yes. Yes. They have OH, NH bonds. And these are the examples that you can memorize. If you have a solvent that is polar aprotic, you don't know OH bond and no NH. That's key. Whoa, I don't know why it's not drawing this one that good. No NH bond there. And these are the exact examples. So you can think of a polar protic solvent as a huggy crowd with OH and NH bonds to hydrogen bond with. It surrounds every ion in a cage of little hugs. That's wonderful if you're trying to help a leaving group depart and a carbocation to stabilize. The crowd comforts everyone, which favors SN1 and E1, but it's terrible for an incoming nucleophile, which gets smothered in hugs and can't freely move, and that slows SN2 down. In a polar aprotic solvent, it's polite, distant crowd. It's still polar enough to stabilize the positive charge from across the room, but it has no OH or NH, as we discussed. For an anion to interact with that. So the nucleophile stays naked, unhugged, unhindered, and free to swing hard and fast the moment it finds its target. And that's what SN2 needs, right? So SN2 needs this. So that is what explains now this chart. So if you have a polar protic solvent or if you have a polar aprotic solvent, and then this is whether you have a strong bulky base or whether you have a strong small base. And so whether in organic chemistry, it's not just about whether you're strong or weak, like in general chemistry. It's also about the size. And organic chemistry considers a lot of 3D shapes as well, right? It's thinking about everything in 3D as well. So that's why you'll see bulky here and small here. So then we have the table. So by this point, you should be able to see that, as it's written here, once your student has all the 6 ideas above, you should be able to understand how crowded is the reacting carbon and who else is in the room. So we will be able to understand this. So we'll read this out. Methyl and primary are open, backside attack is possible, so SN2 is always at least on the table. And secondary is toss up, tertiary is buried. So you don't need to do this right now. You will be able to answer these after you've done what we were doing just above. But the main important thing is how to read this. So notice the pattern. As you go down the substrate column, the carbon gets more crowded. So SN2 gets harder and harder until it's gone by tertiary. So if you notice, SN2 is all here. SN2, 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 methyl, good, primary, secondary. SN2 is still there a little bit, but once you hit the tertiary, it's just gone. And why is that? So as you go across a row towards stronger, bulkier bases, elimination starts to take over. So this is when you get strong, bulky base. Oops, where's that? Strong. Where's my pointer here? For the strong, bulky base, you get E2 more so. And methyl is the one row that never budges. Methyl. It only stays SN2, methyl substrates. There's nothing to protect it from, so it's always SN2. Okay, and then we can also do the recap and rehearsal, but at this point we went over the entire review simply for the 4th chapter. So I hope it gave you a better understanding of than before of everything here. It's a little bit of a more basic review, and then these are questions you can just screenshot and answer yourself on your own terms too. Yeah. All right, everyone. So I took a long break since I've been on here, but let's see, I'm gonna do it in dark mode today. So we have alcohols now for organic chemistry. Now, I know for alcohols, we've already gone over that an alcohol is basically an OH like that, right? And then if you have a diol, it's having 2, right? So we say ol for an alcohol. Wait, I should get the pen so I can write on this. So you have ol for your alcohol, right? But then you use the suffix ol, and it has a general form of ROH, as I'm trying to show you now. So the key thing is that OH there. And if they are not the highest priority group, meaning if this OH is not the highest priority group, remember we already reviewed highest to lowest priority. So if it's not, then it's given the prefix hydroxy, right? And then for phenols, it's a benzene ring. So look at these rings here. A benzene ring basically looks like this with these double bonds. Here, that's benzene. And they have OH groups attached to them, named for the relative position of the OH groups. All right. So ortho looks like this, meta looks like this, and para looks like this. Okay, now we can go on to alcohols can hydrogen bond, raising their boiling and melting points. What does that mean? Well, if this is a little bit confusing, going back to general chemistry review can help a lot, because basically to understand boiling and melting points, you have to get that to raise a boiling or melting point means that you're gonna need more energy in order to break stronger bonds. And because in this case, alcohols can hydrogen bond, which is a pretty strong bond that can form. If you don't understand this, then go back to general chemistry on the chapter on bonding. That means that it would raise, if they're bonding and it's a strong bond, it would raise the boiling and melting point because it would take more energy, require more heat to be able to break those bonds apart. So boiling and melting point basically increase. Phenols are more acidic than other alcohols because the aromatic ring can delocalize the charge of the conjugate base. Electron donating groups like alkyl groups decrease acidity because they destabilize negative charges. Electron withdrawing groups such as electronegative atoms and aromatic rings increase acidity because they stabilize negative charges. So we'll go through that in a second as well. This one we just went over, and this one we just went over. They're a little bit newer, so we'll go over those in a little bit more detail, but we're going to go over to reactions of alcohol. So alcohols can go through reactions. Primary alcohols can be oxidized to aldehydes only by PCC, which is otherwise known as pyridium chlorochromate, and they will be oxidized all the way to carboxylic acids by any stronger oxidizing agents. Secondary alcohols can be oxidized to ketones by any common oxidizing agent. Alcohols can be converted to mesylates and tosylates to make them better leaving groups for nucleophilic substitution reactions. Remember, these nucleophilic substitution reactions we already talked about, SN1 and SN2. So when you have a mesylate that's formed from the alcohol, it contains an SO3-CH3 group. And that's what it looks like over here. SO3, so 3 of these guys, and then CH3 right there. And then tosylates contain this. So SO3 right here, and then C6H4, which is basically like this ring here, and then CH3. So that's a tosylate. And this will make alcohols better leaving groups. Okay, aldehydes and ketones can be protected by converting them into acetals or ketones. Protected as in, let's say you try to do a chemical reaction and you don't want that group to react, you're going to protect them from being part of that. So acetyl is a primary carbon with 2 or more OR groups and an H atom. Ketyl is a secondary carbon with 2 or more OH groups. So deprotection is the process of converting an acetyl or keto back to a carbonyl by catalytic acid. So we'll go into analogy soon if it's confusing, but right now we're in like review mode. Reactions of phenols. Ketones are synthesized through oxidation of phenols. Ketones are resonance stabilized electrophiles. Vitamin K and vitamin K2 are examples of biochemically relevant ketones. Or ketones. Here's an example. Right? So where's some other stuff here? So remember we reviewed phenols, right? So these are phenols. And so when we talk about phenols down here, that's what we're talking about. So they are synthesized via oxidizing these phenols, and then that's how you get a ketone. Hydroxyketones are produced by oxidation of ketones, adding a variable number of hydroxyl groups. That's also a typo over here. Ubiquinone, also called coenzyme Q. So if you remember our biochemistry review on the electron transport chain, that's what we're talking about. If you don't, then you want to go back to biochemistry on that, just so it gives you a better idea what we're talking about when we talk about ubiquinone. And it's another biologically active ketone that acts as electron acceptor complexes 1, 2, and 3 of the electron transport chain, is reduced to ubiquinol. So most of that is memory as well. All right. So there's a few things from here that I want you to take away as some main takeaway points. So again, an alcohol, just think of an alcohol as a carbon chain, as I drew, with an OH or a hydroxyl, that's hydroxyl, hanging off of it, right? And the phenol, you want to think of it as a special case of that alcohol. So it's an OH still sitting directly on top of something, but what it's sitting on top of is this benzene ring. And all of these have a benzene ring. And because there can be more than one OH on the ring, as you can see here, these should have OH at the end, I think so. We can describe the relative positions using these names, right? Ortho, meta, para. So that's what we just went over. So one is next door, one is apart, and one is directly across, apart from each other and next door to each other. Right? So that's the takeaway about those ones. Now, the takeaway about alcohols having higher melting boiling points is because the OH group has a hydrogen attached to it, so it makes it very electronegative, makes it attached to a very electronegative oxygen, so it can donate and accept hydrogen bonds with neighboring molecules. So basically, alcohol can hydrogen bond, okay? And that means they have higher boiling and melting points because hydrogen bonds are pretty strong form of bonds. Okay. And remember, general chemistry review, that H likes to bond with FON, and then fluorine, oxygen, nitrogen, and those would be H bonds. If not, then review general chemistry on bonding. And then phenols happen to be more acidic because phenols, they're more acidic than a typical alcohol because when a phenol loses its proton, its H+, that's its proton, the negative charge left behind on the oxygen doesn't just sit there, it can delocalize into the aromatic ring through resonance. So what we're talking about is this ring here, in which you can delocalize. So an analogy is that if you're standing on thin ice, if your whole weight is on one point, you're skating on thin ice, and your whole weight is on one point, this point here, well, what would happen? Well, if your whole weight is on 1 point, you're in trouble because that's a plain alcohol's conjugate base, basically, with the negative charge stuck directly on one oxygen. Now imagine you can spread your weight across 5 or 6 different points on ice. That's much more stable. So that's why they say that a ring like this is like resonance stabilized. It's stable. Because what it's able to do is kind of like distribute its weight across these points. And that's what the aromatic ring does for the phenol's conjugate base. It spreads the negative charge out. And a more stable conjugate base means a stronger acid. Equals stronger acid because more stable conjugate base. Okay. Where are we on electron donating groups as well? So when we want to decrease acidity, right? Like alkyl groups, they push extra electron density toward that already negative oxygen, right? So they pile more onto one spot, and so they're doing the exact opposite. They're destabilizing the conjugate base, and they make the phenol less acidic. Okay, so that's the idea of this section there. Just a quick overview. I wanted to go over also this part about the biology, about vitamin K1 and vitamin K2. So for vitamin K1 and vitamin K2, they're also important, and these would be cofactors in clotting. So they're important for clotting, blood clotting. So if you don't know what that means, it's good to review biology for this part in particular. But all in all, that's basically it. The rest are pretty much, there's also a better image I could show for this, actually. Let me get that. Here we go. This is like a flow chart, reactions of alcohols. So alcohol can go through oxidation, dehydration, esterification. So as you can see, these are all important to know here, and this gives you a better overview of alcohol reactions. Different major kinds of alcohol reactions are these 3 here. So yeah. Now we can go on to also deprotection. You can think of it as the opposite of protection, right? Anyway, let's go into aldehydes, ketones, electrophilicity, and oxidation and reduction. So the first things first that we're going to start off with is the definition and properties. So first you're going to look at what are even aldehydes, and this is exactly what an aldehyde looks like. This is exactly what a ketone looks like. And in organic chemistry, the pictures, diagrams are really important to know what an aldehyde looks like and know what a ketone looks like. All right, so this R, by the way, means that this chain would be somewhere like doing something else. And so this ketone is not non-terminal. I think we went over what that means before in the video, so I won't go over it again. But the aldehydes are going to be terminal functional groups. Here, it says over here, terminal. All right, and then we already went over nomenclature, so that's a check mark for both of them. If not, the suffix for ketone is -one, and then an aldehyde is -al. And in rings, they're called carbaldehyde, apparently. And then the prefix for ketones, oxo or keto. All right, so that's what a basic aldehyde and ketone are. So the carbonyl is very reactive. Why is the carbonyl so reactive? Well, the carbonyl is a carbon-oxygen double bond. Did you see that, right? Where is this? Carbon-oxygen double bond. And so you have a carbon-oxygen double bond, and this carbonyl it's also polarized. So oxygen is more electronegative, so it hogs the electron density. So this onto this, which is more electronegative. Electronegative. Is it carbon or is it oxygen? Well, well, it turns out that the oxygen is more electronegative, so it's going to be partially positive for the carbon. So the partial positive, the carbon means that would be electrophilic. So it's the site where nucleophiles will end up attacking throughout this entire topic that we're talking about. That same polarity also raises the boiling point compared to alkenes of similar size because you got a dipole-dipole interaction. And so for the oxidation, so this is what it was talking about here, about carbon being slightly positive. And then it says carbonyl-containing compounds have a BP higher than equivalent alkanes. So that's what we were talking about earlier, about having a boiling point, in a sense for boiling point that's higher. And alcohols also have a boiling point higher than carbonyls due to hydrogen bonding. So you can imagine that they are strong bonds if it requires a higher boiling point to break bonds. Oxidation. So for oxidation, this is basically thinking about the last chapter we were talking about, how when you oxidize a primary alcohol, you get an aldehyde, right? So aldehydes and ketones are commonly produced by oxidation of primary and secondary alcohols. So that ties back to alcohols of what we just learned. And so weaker anhydrous oxidizing agents like PCC. So this is a weak agent. Weak agent is PCC. Must be used for synthesizing aldehydes, or the reaction will continue oxidizing to a carboxylic acid. So here you have a primary alcohol. These images are really good for people to learn. Then you have a primary alcohol which turns into an aldehyde when this weak when it's mixed with this weak agent here. This weak oxidizing agent is able to turn it to aldehyde. Okay, so now we can go on to I wanted to go into oxidation and reduction reactions. And the reason why is because, well, we're kind of building off of what we just learned about oxidation. This is oxidation here. And for oxidation reduction reactions, so now we're talking about what can aldehydes and ketones then become. So aldehydes are like two-way streets. They can oxidize further using something like KMNO or H2O2, right? H2O2, KMNO, whatever oxidizing agent. Like they can use another oxidizing agent and then be turned into a carboxylic acid, essentially. So it can go from just being an aldehyde all the way, if you drew another arrow and you put, another agent here, like CrO3, and then that would turn into your carboxylic acid. All right, so that's this part here. And then, or they could be reduced back down to a primary alcohol using a hydride reagent. And these are examples of hydride reagents. And then ketones are one way in oxidation, only one way. So aldehydes can go forward, they can also go backward. Remember, we can have stronger agents, oxidizing agents, or we can have the hydride. And ketones are only one way. So there's no hydrogen left on that carbonyl-carbon for an oxidizer to grab. So a ketone simply cannot be oxidized any further, but it still can be reduced using the same hydride reagents down to a secondary alcohol, to alcohol. So here you go. Here's a nice chart that kind of summarizes what we were just learning earlier. So here's oxidizing agent that can be used, and here are reducing agents that can be used. Reactants and their products. Okay, well, this chart is a really nice summary. All right, now we can move on to, I hope the microphone's not capturing all the rain, but it's like a rainstorm outside. All right, anyway, sorry. Nucleophilic reaction is basically unifying what we were learning, right? So a nucleophile attacks electrophiles, right? Like anything that's electrophilic kind of thing. So a nucleophile will attack an electrophilic carbonyl-carbon, and that will end up forming, so forms a bond. And so forms a bond. So the electrons in the pi bond get pushed off onto the oxygen. Okay, so it's pushed off onto the oxygen, and what happens next depends entirely of what's already attached to that carbon. So if there's no leaving group, like an aldehyde or a ketone, where the only other substituents are H or alkyl groups, the carbonyl just stays open, so will remain open. So if there's no leaving groups, the carbonyl will remain open. Right? That oxygen gets protonated, so it has an H plus protonated, and you're left with an alcohol. So to form an alcohol. And so you're left with an alcohol, but if there's a good leaving group already on that carbon, like a carboxylic acid and its derivatives, as it says here, those are good leaving groups, the carbonyl will reform and kick off the leaving group. So the carbonyl reforms as this and ends up kicking off that a leaving group. So you can think of the carbonyl-carbon as a rotating door, right? So you ever been through a rotating door where it spins in circles? And so the nucleophile pushes open that door, and if nothing was ever attached that's able to leave, the door just stays propped open, and that's your alcohol product. But if something attached was already primed to exit, the door swings back shut behind it, ejecting that group. And that's what happens with carboxylic acid derivatives. Aldehydes and ketones almost always land in the door stays open kind of category, so it'll always leave that door open. But that's just an analogy. So for hydration reactions, water adds to a carbonyl leading to a geminodiol. We already know what a geminodiol was because I went over that before. And if you don't, well, the review is right here. Here's a geminodiol. So you have two alcohols, but they're attached to the same carbon here. All right, and would be a hydration reaction. You can think of hydration reaction as just adding water. You're getting yourself hydrated, so this organic molecule is getting hydrated, right? So that's one way to think about that. So now aldehyde plus alcohol. So when you get, into hemiacetals, acetyls, hemiketones, and ketones. So this is the reverse of D-protection reaction from last time. So we had a D-protection reaction here. The process of converting an acetal and ketoacetal back to carbonyl bicatalytic acid. That you can think of it as the opposite. So you can basically react one equivalent of alcohol with an aldehyde. One equivalent of alcohol with an aldehyde. See, I'm not circling this well. Here's alcohol plus the aldehyde, and you get a hemiacetal, right? And so you have the hemiacetal and one OR group and one OH on that carbon, right? You see that? One OR and one OH ends up on that carbon. So now if you do the same thing with a ketone, you get a hemiketo, which is over here. So if we did that same thing, mix this with this, and this is the alcohol, you get a hemiketo, right? Now, if you add a second equivalent, this is our second equivalent, second EQ of alcohol. Also, if you don't understand what equivalent is, that's general chemistry review, so doing general chemistry is important first. If we add any of our second equivalent alcohols, we then get an acetal, or in this case below, we get a keto, right? So studying these diagrams can help you understand what this is saying. This is basically just saying what the diagram is saying and what I was just saying. So if you add that second equivalent alcohol, the hemiacetyl or the hemiketo converts through a nucleophilic substitution. So remember, we learned about nucleophilic substitutions already, kicking out that first OH as water into an acetyl or ketyl with 2 OR groups on that carbon. So 2 of these on a carbon, and the carbon would be in the middle here. Okay, so now we can get into nitrogen. So nitrogen plus a carbonyl. So nitrogen can be an attacker too, and that will lead to what we know as imines and enamines. So a primary amine can act as a nucleophile instead of an alcohol. It attacks a carbonyl. So here's a primary amine, and it attacks a carbonyl, and instead of this, you get this, which is what you see here, an imine. The same basic chemistry with slightly different nitrogen-containing reagents also gives you oximes, hydrosomes, and semicarbosomes. All right, so they're all kind of like cousins of imines here anyway. So they're all similar. And so imines can also tautomerize, as it says here. Imines can tautomerize to form enamines. So imine, this is tautomerization happening over here. Tautomerize. And so what that means is that you can shift the hydrogen and the double bond around. So it's basically shifting around, right? And then it shifts around to become an enamine, where the double bond moves off of the nitrogen. So before we have this double bond with the nitrogen, clearly. Trying to make it more clear. We have C double bonded over here to N, right? Over here. But over here, it's C double bonded to C, right? So that's something to notice. And now you can think of it as an imine and its enamine are like 2 snapshots of the same coin flip. The double bond and the proton just trade places, so the nitrogen versus the neighboring carbon, but it's the same atoms, they're just rearranging, right? So that's tautomerization happening there. Now we have this HCN, right? Here, hydrogen cyanide. So cyanide can attack as well, and it's last on the nucleophile list. Nucleophiles. We're talking about nucleophiles, by the way. Nucleophiles. And so the cyanide carbon attacks the carbonyl carbon. This is the carbonyl carbon. This is attacking. This would be your cyanide, right? So the cyanide carbon attacks the carbonyl carbon, pushing the electrons onto oxygen. So that's why this arrow is going to oxygen, because it's pushing the electrons. Electrons are going to the oxygen. Now all of a sudden we see this oxygen is negative because it got all the electrons pushed onto it, right? And so now we have, more negative oxygen here. And what that forms is called an alkoxide, which then grabs a proton, and the product is then cyanohydrin. So a carbon would now have both an OH and this cyanide here. This cyanide looks like this, CN, and it has this OH as well, right? So that's what you get. All right, so that's basically all of that chapter, and then I'll see you guys on the next one if I can navigate to it. All right, let's go. Okay, everyone, so now let's go over analyte and aldyl chemistry. So we're going to be going over aldyl, enolates, how aldehydes and ketones kind of have to do with this. Oh, my Windows security. All right, so last time we were talking about the carbonyl carbon. The electrophile is the thing that nucleophiles like to attack. And today we're going to flip the script, and we're going to kind of build a nucleophile out of a carbonyl containing molecule using the carbon right next door. And that's the whole idea behind enolates. That's the whole idea behind enolates. So enolates, what else did I wanted to say about enolates? Once you have kind of a nucleophile built from that carbonyl, you can react it with another carbonyl's electrophilic carbon, and then that's what an aldyl reaction is. And I'm just going to repeat that. So once you have a nucleophile built from a carbonyl, you can react it with another carbonyl's electrophilic carbon and get, and essentially that's what aldyl condensation is. So 2 carbonyls, one playing nucleophile and the other one playing electrophile, right? And they form a brand new carbon-carbon bond. So let's basically go over alpha carbon, alpha hydrogens, what they are, so general principles, because that makes the most sense to read this review sheet. Most stuff is like left to right, basically. I don't know why it's, okay, they're alpha carbon and alpha hydrogen, so you can see alpha carbons here, and the alpha hydrogens are these ones. Now, so the carbon sitting right next to the carbonyl is the alpha carbon. The hydrogens attached to it are the alpha hydrogens, and the one carbon further out, the beta carbon and the beta, so beta carbon is just beside the alpha carbon, and then you have your beta hydrogens, and then you have these were your alpha hydrogens, right? And then where's the carbonyl, right? Carbonyl is just like this. Okay, so that's what happens. So that's some basic structure. So why are the alpha hydrogens then acidic? The alpha hydrogens are acidic, and so the key idea is that the entire thing is normally a CH bond is not acidic at all. But an alpha hydrogen sits next to a carbonyl, and that carbonyl oxygen is electron withdrawing. This one. Electron withdrawing. Right? So it's electron withdrawing, and so it's constantly pulling electrons density away, which weakens the CH bond right next to it, and it makes the hydrogen surprisingly easy for a strong base to remove. So this alpha hydrogens come easily removed by a strong base. So that's what's happening there. And that's why we have electron withdrawing O, as we just talked about. The carbonyl weakens CH and alpha hydrogens. The enolate resulting from the deprotonation can be stabilized by resonance with the carbonyl. So in other words, the strong base can remove the hydrogen, right? And once it's removed, you're left with a negative charge on that alpha carbon, on this carbon here. And so you're left with that negative charge, and that's known as a carbanion. So it's C minus, carbanion. It has this negative charge, C minus. And so you're left with this carbanion, and it doesn't just sit there exposed like that. It can resonate with the adjacent carbonyl, delocalizing the negative charge. So this is what we mean by that deprotonation can be then stabilized. So it can then be stabilized, and that resonance stabilized species is called an enolate. So it's resonance stabilized is what it was trying to say here. All right, so that's good. And now ketones are less reactive toward nucleophiles than aldehydes, and now we can explain why. And the first reason why is because of sterics. A ketone has 2 alkyl groups crowding the carbonyl carbon instead of just 1. So steric hindrance. And so there's a lot of bulk. So steric hindrance, you think of bulky or small, right? In this case, we're thinking of there's a lot of bulk in the way as a nucleophile tries to approach, and that raises the energy of the transition state. And the second thing that happens is the electronics. So again, the transition step and increases energy. And the alkyl group also donates electron density to carbanion, making it less stable. So in this sense, the alkyl groups are electron donating, and if a carbanion or an enolate forms nearby, extra electron density being pushed in only destabilizes the center that's already electron rich. So let's do an analogy. It's like you're trying to park a car in a spot that's already got 2 extra cars nosed in from either side, and it's hard to get into, right? So if you're already carrying extra cargo you don't want, and the last thing you need, so that, by the way, that would be your sterics, right? Bulky, something bulky, or the 2 cars, in other words, in the analogy, is blocking off any of that nucleophilic attack and reaction from occurring like that. And if you're already carrying extra cargo that you don't want, the last thing you need is someone helping you load in more of it. So that is kind of like the electron donation destabilizing the carbanion. Okay, now we can go on to keto and enol tautomers, which would be here. So for keto and enol tautomers, aldehydes and ketones don't just exist in this one fixed structure. So we have keto and enol. Aldehydes and ketones can exist in a keto form and an enol form. So the keto form, as it says, is more common. So the keto form is with this CO intact, as you can see right here. But if you compare this one, it doesn't have that, right? So the enol form has that oxygen and double bond shifted over. The alpha hydrogen moves onto the oxygen, and the C double bonded O, right, becomes just C double bonded to C, which is right here. Okay, so that's what's happening there. So these 2 forms are called tautomers. So they're isomers. So we already been through the isomers chapter that can be interconverted by moving a hydrogen and a double bond. So we went through that already, and they are tautomers. Okay, awesome. So now we have things about kinetic versus thermodynamic enolates. So if you don't know the word kinetic product versus thermodynamic product, you need to review it from general chemistry, because that's your foundation, or you can just listen up a little bit here. So for kinetic versus thermodynamic enolates, when a base removes an alpha hydrogen, and there's more than one type of alpha hydrogen available, which one comes off first actually depends on the reaction conditions. So the kinetic enolate forms very fast. Kinetic products in general chemistry, as we learned it before, they happen very fast, whereas thermodynamic is slower, but it's slower but more stable of a product, whereas kinetic products are less stable, but they form faster. So that's just the general chemistry review. General chemistry chem review. So when you have this thermodynamic versus kinetic enolate. So when you have this kinetic enolate, it's favored by fast irreversible reactions at low temp with strong sterically hindered bases, favored by slower reversible reactions at high temp with weaker, smaller bases. So the enolate that's kinetic forms fast under low temperature using a strong bulky base, and the reaction is irreversible. The base just grabs whichever alpha hydrogen it's able to reach, so alpha hydrogen. And the thermodynamic enolate forms under high temperature with the weaker base, smaller base, in a slower reversible reaction. Given enough time and enough reversibility, the system settles into whichever enolate is most stable, as I said here. All right, which is typically the more substituted one. So, enamines, actually we should go into, enamines are tautomers of imines, like enols. Enamines are less common tautomer, so as you can see here. And so Michael addition, one more preview before we get into aldol chemistry. An enolate, right, our new nucleophile, Nu minus is how they kind of notate it sometimes. Our nucleophile can attack an alpha beta unsaturated carbonyl, forming a new bond, right? So that's basically what it is. And that's a Michael addition conjugate addition of an enolate nucleophile onto an enone electrophile. So we'll learn more about this when we go into aldol reaction, which we're going to do right now. So for the aldol condensation, we are building an aldol, in other words. So let me just move over. So think of this as building an aldol. So we're building an aldol. So now we can try to combine everything. An aldol condensation starts with an aldol addition. Aldol addition to create an aldol and a carbon-carbon bond here. So one molecule of aldehyde or ketone gets deprotonated at its alpha carbon to form an enolate. That's our nucleophile. That enolate then attacks the carbonyl carbon of the second aldehyde or ketone molecule, still sitting in its normal keto form, and that's our electrophile. This is the exact nucleophilic addition mechanism since the last chapter, just with like the nucleophile generated in the house itself rather than added in separately, right? So the result is a brand new carbon-carbon bond, right? And the product called aldol, right? Literally ald, right? Like from aldehyde, and then ol from alcohol, and that's what the aldol looks like. So because it contains an aldehyde or ketone, by the way, so ketone, it could be or ketone, carbonyl, and an alcohol and adjacent carbons. So for dehydration is when you can turn from an aldol to an enone, right? So the aldol doesn't just have to stop there. What can happen is that under continued base and typically heat, the aldol loses a water molecule and it goes through a dehydration reaction. Dehydration, which is right here. So after the aldol's form, a dehydration reaction can occur, and this results in alpha beta unsaturated carbonyl. And this is also called an enone. All right. So again, two acetones under any where is this? Two acetones. So this is what we're talking about when you can have an aldol reaction and then a dehydration can occur, which is also called an enone. And so two acetones under NaOH. Oh, this is so weird. Okay, sorry, I just was practicing something. And two of them under NaOH first do an aldol reaction forming a beta hydroxy ketone, and that's an aldol. This, an aldol. And then from there we get an enone over here. And that's basically after we've been able to go through a second round of, it's kind of messy here, a second round of NaOH. So first round is here and second round is there. So yeah, that's what happens over there. And then we can go into retro-aldol reactions over here. So the retro-aldol reactions is the reverse of aldol reactions. So what can happen is a retro-aldol reaction is catalyzed by heat and a base. And it cleaves the bond between the alpha and beta carbon, literally undoing the aldol addition, breaking that new CC bond, the carbon-carbon bond we just formed, and regenerating two separate carbonyl-containing molecules. So it's just rewinding the tape, right? So it's a reverse reaction. Not an arrow there. Not an arrow there. Okay. So that's basically the entire part on, whoa, why did you get so far down? That's the entire part for the chapter 7 aldehydes, ketones. And next we're going to go on to chapter 8 carboxylic acids, which is going to be very interesting. And then their derivatives, which is going to be very interesting. And so we'll get onto those two chapters after I take a break. And maybe you might want to too. Okay, so we're going to go over the carboxylic acids now. So carboxylic acids, organic chemistry 8. So what are carboxylic acids? Carboxylic acids contain a carbonyl and a hydroxyl group bonded to the same carbon. So here's a carbonyl group, and then this is the hydroxyl group. And so you'll notice that they're always going to be at the end of the chain. Like let's say this R group was a really long chain that looks like this. This would always be terminal. So at the very end of the chain. The nomenclature is to use oic acid. So yeah. Salts are named with the suffix OA, and dicarboxylic acids are dioic acid. So that's when you have two carboxylic acid groups on the same molecule, and you get, it's similar to diol, right, for alcohol, but that's for alcohols. Diol, or you just add di, and that means two. All right, so for physical properties, carboxylic acids are polar and they hydrogen bond well. Pretty, not just well, but extremely well, and both the OH and the carbonyl oxygen can participate. That gives it very high boiling points, and so that's even higher than alcohols in comparison, because in solution, 2 carboxylic acid molecules will often pair up to form dimers in a solution, and each one donating and accepting like a hydrogen bond, right? So, and because we know hydrogen bonds are so strong, right, that makes it very high boiling points and melting, just boiling points. Yeah, so BP is boiling point here. What else do you want to know? Why are carboxylic acids so acidic? That's another thing. So this should be kind of familiar by now, but when a carboxylic acid loses its proton, the resulting charge doesn't just sit on one oxygen, it delocalizes through resonance between its oxygen atoms, between many atoms. So the acidity can be further enhanced by substituents that are electron withdrawing and decreased by substituents that are electron donating. So one way you can think of it is that it's the same idea about thin ice and the phenols, remember? So when you spread your weight, like in this case, it's like spreading the negative charge across many points, and it makes the one whole thing, or the one whole molecule, more stable, right? That's how you can kind of think of it. And then for beta dicarboxylic acids, this is kind of related to enolate chemistry. Enolates, remember we were talking about enolates. So when 2 carboxylic acid groups sit 1,3 to each other, basically a beta dicarboxylic acid, right? This is what that is, a 1,3 dicarbonyl compound. The hydrogen and the carbon between them, the alpha hydrogen becomes highly acidic. This is highly acidic, the alpha hydrogen, deprotonated, and then the resulting thing you get is a carbanion. And so the resulting carbanion can resonate with not just one, but both adjacent carbonyls. So here. Okay, so alpha proton is the most acidic due to resonance. Okay, so now we can go into making carboxylic acids through oxidation, which is over here. You can make carboxylic acids through oxidation. So this is kind of related to the aldehyde chapter, where we can oxidize a primary alcohol or an aldehyde with a strong oxidizer, and it doesn't just stop at the aldehyde, it keeps going until you get a carboxylic acid. So it keeps going till you get carboxylic acid, and you can also oxidize something that looks like benzene, so it's kind of like something like benzene, type of primary or secondary alkyl group directly on a ring, as shown here with KMNO4 as the agent, right? Converting a methyl group straight to a carboxylic acid on the aromatic ring. So this is a straight form of doing it. Okay, next thing you can have is a nucleophilic acyl substitution. So I'm going to go right over here. So for the nucleophilic acyl substitution, I didn't see nucleophiles over here. And so a nucleophile attacks the electrophile attack. And so remember, that brings the electron, pushes it up to the oxygen. It pushes the pi electrons onto the oxygen, and it forms a tetrahedral alkoxide ion intermediate, what it says right there. And then, but this carbon already has a leaving group. It has a leaving group, so this is the leaving group. Y is the leaving group, right? So instead of that intermediate staying open as an alcohol, the carbonyl reforms a CO bond, which is right here. And then Y gets kicked out. Yeah, that's basically what happens there. And then the next thing is amides, esters, and aldehydes. So amide, anhydride ester. So we're going to go through those as well. Let's see how I want to do it so it's more like flowy. So we can go through nucleophiles here. So for the nucleophiles, remember, you can swap in different nucleophiles, but you'll end up with different products, all through the same substitution mechanism. So ammonia/amine. So ammonia or an amine attacking gives you an amide, forms an amide. Amides are given the suffix amide, yeah, and the cyclic amide is called lactam. And so the alcohol can also give you an ester, and an ester has a suffix OH, and a cyclic ester is lactam. Now, a carboxylic acid attacking gives you an anhydride, and both linear and cyclic anhydrides are both called anhydrides, so that one is simple enough to name. Now, if you go into your, the acid halide synthesis, right? So basically, before any of these, though, it's common to first convert the carboxylic acid's OH into a much better leaving group. So if we do that, in this case, it would be chlorine. So this thionyl chloride over here, this over here, is more reactive. They're basically very reactive electrophiles. So they make the substitution with the weaker nucleophile go faster. And yeah, that's a leaving group there. Acid halide synthesis. So I just wanted to know this is related to mesylate, and tosylate that we were learning earlier. Tosylate. Whoa, It's hard to see my rating there, yes. But basically, it's like swapping out a mediocre kind of leaving group for an excellent one before you actually need the substitution to occur. And so that's what's happening there. And then next, for amide synthesis, this is how your body kind of builds proteins. So you have 2 amino acids coupled with the DCC, and that will then give you a dipeptide. So DCC is the activating agent. It's the agent. And so it will form an amide bond between the carboxylic acid of one and the amide of another, right? So this one and this one are then gonna connect together, which is over here. So what's happening over here. Now, if we go into anhydride synthesis, you will heat 2 carboxylic acid molecules together, and one acts as a nucleophile attacking the other, kicking out water, and then forming the anhydride. So this is the heating, kicking out the water. So the water is getting kicked out of this big thing, and this is basically 2 carboxylic acid molecules together, right? That's what it looks like. So for ester synthesis, ester synthesis, esters can also form the other way around. So instead of the alcohol attacking the acid's carbonyl carbon, here the carboxylate oxygen itself it acts like the nucleophile in a straightforward SN2 reaction. So attacking the electrophilic carbon of an alkyl halide and displacing the iodide. This iodide gets kicked out basically, right? And so now this is here in place. Yeah. All right. So yeah, learn about SN2 reactions again if you need to, and it'll kind of make a little bit more sense. All right, and then we can go on to reduction. So how we can everything can back down and become a primary alcohol, which is over here. So we can do the opposite. Instead of making carboxylic acids and doing all the synthesis and stuff like that, we can also go back down to a primary alcohol. And so reduction kind of runs this whole story backwards. So you can have a strong reducing agent such as LiAlH4, and it delivers a hydride to the carbonyl carbon, kicking out the original leaving group, right? So, and then it forms an aldehyde. So this is the aldehyde. But that aldehyde doesn't get isolated. It's immediately hit with a second hydride forming an alkoxide ion, which then gets protonated on the workup with H3O. So protonated. H plus basically, and then to give the final primary alcohol. So notice that NaBH4 isn't strong enough to do this reduction at all, right? Carboxylic acids are relatively poor electrophiles compared to aldehydes and ketones, and since that resonance stabilized carbonyl is already pretty content, you need to have something like LiAlH4, which is the ones we're using here, something very strong, right? A hydride donating power to force that reaction through, and you have to do it twice in a row, 2 times for it to happen. Okay, so that was reduction. See, NaBH4 is not strong enough to reduce, and that's what I was just talking about. And then now we can go into decarboxylation. So beta dicarboxylic acids and other beta ketone acids can undergo spontaneous decarboxylation when heated, losing a carbon as CO2. This reaction proceeds via a 6-membered cyclic intermediate. So think of it as a 6-person circle passing along a hot potato around in one smooth simultaneous motion. And so proton transfer and bond breaking happening together in one concerted loop rather than kind of like separate steps, right? So the beta dicarboxylic acids and the beta keto acids are generally, they can spontaneously just lose a carbon as CO2 when it's heated. So that's what we know as decarboxylation, just losing a CO2 when it's heated. When the molecule is heated, it's able to lose the CO2. Okay, and this proceeds through a process of a 6-membered cyclic transition state where the carbonyl oxygen of one group reaches around and grabs acidic alpha proton that we talked about earlier, while the carbon-carbon bond to the departing carboxyl group breaks. And then the CO2 will finally just leave, right? Okay, last but not least, saponification micelles. I've seen this several times. You'll see it, I think, also in biology when you talk about membranes and stuff. But for saponification, what's basically happening is you mix a long chain of carboxylic acids, basically a fatty acid, with a strong base, and that results in the formation of a salt that is called soap. And so soap looks like this, and we call the structure a micelle. Micelles have polar heads on the outside and nonpolar tails, which point towards inside. And so the inside of our soap is able to trap grease within the structure. So the micelle has this polar heads, and the grease fits inside the structure because you can think of fat as nonpolar, and like to be together. So nonpolar. And so we can trap that, and then H2O will essentially wash away all that grease, right? So that's kind of how soap works in the first place. And then the organic chemistry part of it, not just like simple biology, is that you get the soap, and a soap molecule has a hydrophilic carboxylate head and a hydrophobic alkyl tail, to be more like specific. And that's pretty much it for saponification. So then we can go into carboxylic derivatives, things that derive carboxylic acids. And then after that, we will be going into nitrogen and phosphorus containing compounds. So amino acids will be related to that. So this will also be useful for you to review amino acids from biochemistry, because then it would help understand structure synthesis of amino acids. But it's not necessarily the case. But this topic will be about amino acids. So going over what are amino acids would kind of help in that way. So we'll take a small break and I'll come back. Okay, so let's go over carboxylic acid derivatives. So last time we just looked at amides, esters, and hydrides through nucleophilic acyl substitution. But today we're zooming into those three products themselves. We're not just saying that they show up here and there. We're looking at more specific. So the first thing we're doing is naming amides. So amide is the condensation product of a carboxylic acid with ammonia or an amine suffix is amide, and if a nitrogen carries extra alkyl substituents, those go at the front of the name, so N, since they're attached to nitrogen. So N kind of stands for nitrogen, that's how I remember it, not to the main carbon chain. So yeah, and then a cyclic amide is a lactam. We talked about lactams before, and it's named with the Greek letter of the carbon forming the bond with the N. So then we have esters. Esters are the condensation products of carboxylic acids with an alcohol, and that whole process is called Fischer esterification. So esters are given the specific suffix OAte, and the esterified group is as a substituent without a number. Cyclic esters are called lactose. And they're named by ring size plus the Greek letter of the carbon bonded to that ring. Oxygen and triacylglycerols, the fat stored in your body, are simply glycerol linked to three fatty acids through separate they're done through three separate ester bonds, is what I was trying to say. So there's examples of them. I recommend doing your own practice questions on them online. There's probably some sort of organic chemistry generator. I used to do that when I was practicing. So I recommend doing it by diagram, if you can find kind of diagram type of practice online. An anhydride is a condensation dimer of two carboxylic acids. A symmetric anhydride built from two identical acids is named for the parent acid plus anhydride, and an asymmetric anhydride built from two different acids lists both the parent acids alphabetically and then writes like anhydride. So yeah, that's how you name them. And then cyclic anhydrides are called dioic, so synthesized by heating dioic acids. So when you heat dioic acids, you get cyclic anhydrides, and just like with lactams and lactones, they are also 5-6 membered rings, and they're generally stable. Okay, so you have to know what these are and how to name them, basically. Now we're going to go over the reactivity order. So this is the ranking you need to be memorized. So you get basically acid chloride and anhydride, esters, amides, and carboxylate. So in this order specifically, this is a ranking, and so it's from most to least reactive toward nucleophilic acyl substitution. So if something's really reactive, it would be on the left side, like acid chloride, for example, but if it's not, it'd be on this side. And so steric hindrance is when you have let's just talk about the order still, because maybe we need to explain it out. So the reason why the order runs this way is because it traces back to the leaving group ability. So in acid chloride's leaving group, which is chloride, remember we saw chloride as a leaving group before, right? So if I go back here, right, chloride can be a leaving group, and so we've seen that happen before. And chloride's leaving group, which chloride is an excellent leaving group. It's a weak base, stable on its own, and it's happy to leave. So that carbon stays highly electrophilic and reactive. So if you walk down the list slowly, or the ranking, and the leaving groups get progressively worse, basically. A carboxylic leaving group would be a strong base and extremely reluctant leaving group, which is exactly why carboxylic salts are basically unreactive towards substitution. For an analogy, this is a mesylate tosylate kind of logic from way back when we were talking about them, but it's running from the opposite direction. So in a mesylate tosylate, we had a bad leaving group that we made it into a good one to speed up the reaction. But here, the identity of the leaving group already attached is what's setting how fast the whole molecule wants to react in the first place. And a good leaving group practically pushes that door open for you, but a bad leaving group holds that rate of reaction, slower. It holds it down. And so steric hindrance, remember about bulkiness and stuff like that. Bulkiness, remember 3D molecules are in 3D, right? In 3D space. And so reactivity isn't always about the leaving group, though. There's other three factors, right? So there's steric hindrance, where bulky substituents crowding the reactive carbon-carbon can slow a reaction down. So protecting groups such as acetyls can increase steric hindrance or otherwise decrease the reactivity of a particular portion of the molecule. So that's how protecting groups are also relevant to that. Induction is another factor. So this is factor 1. Induction is another factor 2 now. And so induction is an even distribution of charge across a sigma bond caused by electronegativity differences. So the more electronegative groups attached near a carbonyl, the more inductively electrowithdrawing pull on that carbon, right? And then the greater its reactivity, because that carbon becomes even more electron poor and electrophilic. So this electronegativity. And so a good way to think of it is like, this is like the same effect of electron withdrawing group effect from the acidity discussions from before. So electronegative atoms pulling electron density away, right, and stabilizing a nearby negative charge. So it's kind of like the same effect over here, where just showing up here as a reactivity boost on the carbonyl carbon instead of like an acidity boost on the conjugate base. So induction again refers to uneven distribution of charge across a sigma bond because of differences in EN. So the more EN groups in a carbonyl containing compound, the greater its reactivity. So that's the second factor. And then the third factor is conjugation. So conjugation is like alternating single and double bonds, which lets the pi electrons delocalize through unhybridized p orbitals above and below the molecule. So exactly, it's like the resonance idea that we've been going over and over again, but it's framed in terms of orbitals here. So a conjugated carbonyl remember that conjugation has much to do with resonance, right? Resonance. Remember that too. A conjugate carbonyl containing compound is more reactive because the same delocalization can stabilize the transition state as the reaction proceeds, lowering the energy barrier to get there. So again, it's the thin ice like analogy one more time, but it's just applied to transition state instead of the final product. So it's spreading electron density all over several p orbitals, right? Remember your quantum numbers and stuff, p orbitals, and it makes that in between halfway reactive structure, which is more like comfortable to pass through, so the reaction gets faster. It's conjugation in a benzene. All right, and then we can have ring strain. So what can ring strain do to our reactivity? So ring strain, if you have increased strain in a ring, so increase the strain, it makes the molecule more reactive, as it says here. So beta lactams are the classic example, and they're unusually prone to hydrolysis because of significant ring strain. So how does the ring strain happen? Well, you have two components of ring strain. You have this torsional strain, and you also have the angle strain here, two types of strains there. And so the torsional strain is from eclipsing interactions between substituents that can't rotate away from each other in a small ring. And an angle strain is from bond angles compressed below the ideal angle, 109.5 degrees. So you can think of it as like a four-membered ring is trying to sit four people around a table built for a much smaller group. So everyone's elbows are jammed together, that's their torsional strain, and everyone's stuck at that uncomfortable tight angle to their neighbor, and that's angle strain. So angle deals with angles, right? And torsional deals with eclipsing, so overlapping. People are overlapping each other. So that's why the analogy is about everyone's elbows are jammed together. In other words, they're kind of overlapping. The whole system is under tension and just waiting for a nucleophile to come and relieve that strain by breaking that ring open. So that's why ring strain makes it more reactive. Okay. And now we can go into the whole mechanism of Fischer esterification. So for Fischer esterification, we're going to go over basically in this one how an ester forms, step by step. So that's what this mechanism kind of shows you. So the first things first is that an acid protonates the carbonyl oxygen, and the acid protonates the carbonyl oxygen and making the carbon even more electrophilic. Right, and the alcohol's oxygen then attacks as a nucleophile. So this would be your nucleophile. Then attacks as your nucleophile, forming a tetrahedral intermediate with a positive charge. So as you can see, this has a positive charge. And so, yeah. Where are we at on this positive charge? And a proton transfer moves that positive charge over to one of the original hydroxyl oxygens, turning it into a good leaving group, which is a protonated water. So this is water over here. Water is a good leaving group. Okay, and then that water then leaves, regenerating a carbonyl, and this time it is attacked by a new OCH3 group. So that's your OCH3 group. And then it's stabilized by resonance. Resonance stabilized. Remember resonance? The resonance is so important to learn. A final deprotonation removes the extra proton, and you're left with a neutral ester. So this leaves, basically. Deprotonation. And now you get a neutral ester. All right, so this is basically a new nucleophilic acyl substitution happening. So again, you protonate to activate the electrophile and let the nucleophile attack, then protonate the old leaving group to turn it into something that actually wants to leave, and then you let it go. And every step is just making somebody either a better electrophile or a better leaving group at exactly the right moment, and that's the reaction, basically. Now we have anhydride synthesis via carboxylic acid condensation. So 2 carboxylic acid can condense directly. So here we have this carboxylic acid plus this carboxylic acid, right? So one acid's hydroxyl oxygen acts as a nucleophile. So this one acts as a nucleophile. And nucleophile is going to attack this carbonyl carbon of the second acid, forming a tetrahedral intermediate. Here's your intermediate. And so the loss of a protein, it's too late for this. It's a loss of a proton, not a protein. Then you have a loss of a water. So loss of water, you also have a loss of a protein that occurs. So proton, sorry, I keep saying protein. Proton is lost here, as it says, and you also lose water along the way. And so that reforms the carbonyl and produces your anhydride. An anhydride looks like this. CO, CO. Probably the image is just better to look at. It's basically this image right here. That's it. That's your anhydride. Anhydride. Right here. That's your anhydride. I was trying to redraw it. That was an epic fail. And then we have nucleophilic acyl substitution. Just last block we have to go over, I think. Yep. Awesome. So we're almost done this one already. That's awesome. So all of these carboxylic acid derivatives can undergo nucleophilic substitution themselves. Nucleophilic substitution reactions. And so the rate simply follows that reactivity ranking from earlier, this ranking here. The rate will just follow that. So the speed at which the reaction is. And so cleavage is when an anhydride reacting with ammonia, an ammonia or an amine gives an amide. Amide. Yeah. And so you get ammonia or an amine will give an amide plus a carboxylic acid. Carboxylic acid. And the carboxylate half is just left out. It's simply the leaving group that got kicked out, basically. And if you react it with an alcohol instead, it results in an ester and a carboxylic acid instead. And if you react it with water, you actually get 2 carboxylic acids. So that's cleavage here. Transesterification is one ester trading its alkoxy group for a different one. So the attacking nucleophile is an alcohol, substituting in for whatever alkoxide there was originally. Amides, we can go into amides. They can be hydrolysed back into being carboxylic acids under strongly acidic or strongly basic conditions, right? And basically, the result of that is like, it's basically the result of sitting near the bottom of the reactivity list, right? So because it's at the bottom of the reactivity list, that's how you can have this to be able, that's why it's strongly acidic or basic conditions. And so the attacking nucleophile here is going to be water or a hydroxide anion, right? All right, so that's about it for carboxylic acid derivatives. So now we can go into chapter 10 on the amino acid. That shouldn't be too bad. Yeah, so we only have 10, and then we have chapter 10, and then 11 on spectroscopy, and then lastly 12 on separations and purifications. So let's go on to 10 first. All right, so for amino acids, basically, we have the anatomy of an amino acid here, where you have basically a carbon in the middle, and it's attached to 4 different groups. You have, this is also called alpha carbon, the central carbon that I just highlighted, and it's attached to the 4 groups, which is the amino group, the carboxylic acid. You have the variable R chain, which kind of defines and differentiates the 20 different amino acids in your body, and then you have this H atom alone. Yeah. So that's your anatomy of the amino acid, and then we can go on to, and all of this, it's chiral in all amino acids of glycine. All amino acids in eukaryotes are L amino acids. They all have S stereochemistry except for cysteine, which is R. So I went over this in the biochemistry review already. So biochem could be useful because I also kind of talked a little bit more about that. But most of that is just memory anyway. Amino acids are amphoteric like water. Water is also amphoteric, meaning they can also act as acids and bases. I went over that in more depth in the biochemistry video. Aliphatic, non-aromatic. So that's when the side chain only contains C and H. So an aliphatic side chain just simply means that, like, exactly, non-aromatic. So yeah, it's only built from carbon and hydrogen. So those include glycine. So these are the amino acids that would be aliphatic. And you just have to kind of memorize that. So glycine, alanine, valine, leucine, isoleucine, proline, and methionine. And then for peptide bonds, that forms by condensation and can be broken by hydrolysis. So if you don't know what peptide bonds are, then it'd be a good idea to review biochemistry again. But that's not so bad, or a review of amino acids. But biochemistry, we did a lot of extensive review on like peptide bonds. So I'll just quickly go over that though. So a peptide bond again can be broken by hydrolysis. So it forms exactly the way we build an amide back in the carboxylic acid chapter. The N terminus, the free amine, the N terminus is the side with literally NH, the amine side, that side with the nitrogen basically. That's why it's called the N side. Of one of the amino acid nucleophilically attacks the C terminus and the carbonyl carbon of another, and that's the nucleophilic acyl substitution happening one more time, basically. So this is basically your nucleophilic acyl substitution happening again. And polypeptides review, if you already done biochem, but polypeptides are made of multiple amino acids linked by peptide bonds. Proteins largely, I don't know what they were trying to say there, are large folded, proteins are large folded and functional polypeptides. So proteins are polypeptides, basically. And so structure synthesis of amino acids is important because that's how we can make amino acids. In the lab, certain standardized mechanisms are used. So we can use structure synthesis, number one, or we can use Gabriel synthesis in the lab. So this is in the lab, not necessarily like in your body, I guess you could say. So our first lab route to an amino acid is basically what we've been talking about in the last 2 chapters. So you start with an aldehyde. Actually, I should show the picture of structure synthesis. Oh yeah, here it is. So you start with the aldehyde, which is this. So you should know what an aldehyde is by now. So you start with that aldehyde, and then ammonia from ammonium chloride attacks the carbonyl carbon, exactly like the amine plus carbonyl reaction that gave us the imine about 2 chapters ago or so. And that imine is then attacked by cyanide, which adds across the CN, the same way cyanide added across the CO bond, and to give the cyanohydrin. So you just swap the electrophile from a carbonyl to an imine, and you get an aminonitrile instead. And finally, hydrolyze that nitrile with 2 equivalents of water, H2O, 2 EQ of water, and that's how this CN group, right, is converted all the way to a carboxylic acid, giving you the finished amino acid. All right, so basically every step of structure synthesis is a nucleophile you already know, right? Or yeah, attacking an electrophile, all right? And so you're chaining 3 familiar reactions in a row. These 3 familiar reactions right now should be carbonyl to imine, right? Then you have the cyanide addition. See, that's how the cyanide gets there, right? Cyanide addition from this. So that's how it gets added there. And then you have the nitrile to the amino acid, finally. Amino acid. So that's basically what's happening there. Now, for Gabriel synthesis, you're building an amino acid as well, but this is the second lab route to do so. So it's even more longer, as you could see, which kind of sucks to kind of try to teach, but yeah. So potassium thialamide, right, attacks diethylbromotein in SN2 reaction. So this is an SN2 reaction. And so you end up with this guy here. And so this mechanism is the exact same as the sodium butanoate plus methyl iodide ester synthesis from carboxylic acid chapter, but it's just that thialamide as a nucleophile instead of a carboxylate, giving that thalamedo-malonic ester. So yeah. And so now you look at the malonic ester carbon, and it sits between 2 ester carbonyls, which makes its remaining hydrogen highly acidic. And this beta dicarbonyl acidic alpha hydrogen from the enolate chapter, it shows up again, and the base deprotonates it, generating a stabilized carbanion. So this is your stabilized carbanion, right? And you have this carbanion, and basically how do I describe it better? Give me one sec though. I want to do this better. So we'll just move from there. Yeah, you have a carbanion, and that carbanion is gonna attack. Okay, so it's going to attack an alkyl halide in a second SN2 reaction. This is your second SN2 reaction. By the way, you read the diagram like that. You just follow the arrows that it's talking about. So you have a second SN2, as it says here, SN2 reaction. So what that does is it gives amino acids R group. So now you get an R group there. And the hydrolysis then does 2 jobs at once. So we have a hydrolysis happening here. Hydrolysis. And so what happens here is that it opens the phthalimide ring up to be a phthalic acid, freeing the amine, and it converts both ester groups into carboxylic acids. Leaving you with a 1,3-dicarboxylic acid sitting right next to the new amine. And because it's a beta dicarboxylic acid, heating it drives spontaneous decarboxylation, the exact 6-membered cyclic transition state that was covered in this carboxylic acid chapter, kicking out one of the carboxyl groups as CO2, and then leaving the finished alpha amino acid, right? So basically, Gabriel synthesis is like a scavenger hunt. And so in SN2 alkylation, an acidic maltonic type of alpha hydrogen, a second SN2, right? So there's a first SN2, then a second one, an amide type ring hydrolysis, and then decarboxylation. You have like 5 reactions that you've already kind of gone over, but now it's like assembled all into one to make this big molecule, or sorry, not big, but to make this one molecule amino acid, to make an amino acid. So basically, if everything you learned in this did not make sense, and your foundation for the other stuff was not as strong, right? So we should know what SN2 is by now and stuff like that. So yeah. So all of this is building up, like since from chapter 1 all the way till 10, it's building up to your understanding of trying to describe this. What is happening to this. So if you go right away from, reviewing and you go right into Gabriel synthesis of amino acid, it's not a bad idea necessarily, but it's good to build your foundations of everything, all the chapters that came before this chapter to get a better idea. But that's fine if you learn it. Everyone learns differently, but having the foundations will help. So the phosphoric acid, now we can go into phosphorus containing compounds. So we're switching our gears fully to phosphorus containing compounds now, right? So phosphorus, phosphoric acid, also called a phosphate group or an inorganic phosphate, like this. That's how it's written. Oh yeah, here. It carries 3 acidic hydrogens, each with a distinct pKa. So at physiological pH, inorganic phosphate exists as a mix of hydrogen phosphate and dihydrogen phosphate. So you can think of the 3 pKa values spread across one molecule means that a phosphoric acid can accept or donate protons comfortably across like a wide range of the pH scale. So then you have your phosphoric acid structure, which looks like that. So yeah, you have 3 hydrogens, each with unique pKa and the pKa values to act as a buffer over a large range of pH values, as we just went over. Phosphodiester bonds now. So for phosphodiester bonds, phosphorus forms the backbone of DNA. So 2 ester type linkages from one phosphate to 2 different sugar molecules. Forming that bond releases pyrophosphate, so PPI, pyrophosphate, which can later be hydrolyzed into 2 separate inorganic phosphates. 3 phosphate bonds are described as high energy for 2 reasons. Adjacent phosphate groups carry large negative charges that repel each other, straightening that bond that holds them together. And once the bond breaks, the freed phosphate is resonance stabilized. So think of this, one more time, the same resonance idea we said over and over and over. A released phosphate spreading its negative charge symmetrically across multiple oxygens is exactly like we've seen before, except here that stabilization isn't just about acidity, it's about energy. And a bond under charge repulsion strain releasing into a resonance stabilized product is a bond that gives up, it releases a lot of energy when it breaks, which is precisely why ATP hydrolysis powers so much of your cell's chemistry. One thing you might want to look at when we're talking about this is biology for cross-bridge cycling. This is biology on the muscle system, basically the chapter on how your muscles work, basically. And then you see the importance of it in terms of like biologically better. So if you relate phosphate to some biological mechanisms you've seen, it might help you learn it a little bit better. And then for organic phosphates, carbon-containing compounds also have phosphate groups. The most notable are nucleotide triphosphates, such as ATP, GTP. If you learned the Krebs cycle, or if you learned about cellular respiration, which is in your biochemistry chapters on metabolism, these will pop up a lot, organic phosphates, because it has to do a lot with your body. So now we can, after this, go into spectroscopy. Awesome. So now we're going into other fun stuff, which is not just organic chemistry in terms of just the molecules. Now we can also look at like laboratory type of things over down here, and it'll be cool. Okay, now we can go into spectroscopy. So that would include IR, UV, NMR, and MR spectroscopy. This ultraviolet is UV spectroscopy. Mass spectroscopy, here's IR spectroscopy. So infrared spectroscopy, in other words. So every chapter so far has been about predicting what a molecule does, how it reacts, and what it will become. But this chapter is a little bit different because spectroscopy is about figuring out like what a molecule already is, right? So it's just by shining different kinds of energy on it and watching how it responds to see what it is, right? And these are the 4 different techniques, so that we'll be going over. And you'll notice something nice, which is a lot of the electron density that we've been learning, especially the electron withdrawing versus electron donating effects, come back here as exact same thing that will explain like NMR spectrum. So it's the same physics, we're just applying it in a different way, in a different light, I would say. So let's start off with IR spectroscopy, which measures the absorption of infrared light, which causes the bonds within the molecule to vibrate. So that's molecular vibration. So you get stretching, bending, twisting, and folding. And it's plotted as a percent transmittance versus wave number, which is just 1 over wavelength. So that's what they're saying here, 1 over lambda, where lambda is wavelength. So the peaks you need to know for the MCAT, so it would be on a graph, is what it's saying. So that's why it's plotted, it's a graph. So these are graphs. So these are good examples of the graphs. here are 3 different examples. There's one for cyclohexanol, benzaldehyde, and cyclohexylamine. So then you have these useful peaks on this graph that you can you basically have to memorize them. So the ones you have to know is NH, which shows up around 3,300 as a sharp peak. OH is a similar region, and basically spectroscopy is showing you the bonds within that molecule, right? So if a chemist ever had like an unknown molecule, they could just, get a spectroscopy and figure it out, right? And so these are the ones you want to memorize and know, like, what type of peak is it. Is it broad? Sharp means it's like sharp, literally. Broad means it goes over a longer range, right? Okay, so I hope that was all right, and these would be examples of what it looks like. So again, on the x-axis you have your wave number, and on the y-axis it's the percent transmittance. Okay. And then for ultraviolet spectroscopy, it's most useful for studying compounds with double bonds and heteroatoms that contain lone pairs that create conjugated systems. So it measures absorption of UV light. So molecules will absorb UV light, which moves electrons between their molecular orbitals, and it's plotted as a percent transmittance or absorbance. It could be either one over wavelength. So you generally plot it as percent transmittance, absorbance versus wavelength. And so for a molecule to show up on the UV spectrum at all, the energy gap between its HOMO, which is the highest occupied molecular orbital, versus lowest unoccupied molecular orbital, has to be small enough. So the difference between HOMO and LUMO has to be small enough that an electron can actually jump across it. And the smaller that HOMO-LUMO gap, the longer the wavelength of light the molecule can absorb. So that's what we're seeing here. Small enough energy difference needed. Okay, now we can go on to NMR spectroscopy. So NMR spectroscopy measures how a nucleus spin aligns with an external magnetic field. And that alignment depends on the local magnetic environment around the specific nucleus. So in other words, what is happening chemically nearby. And that makes NMR like the go-to when you're trying to figure out a compound's actual connectivity and its functional groups. So useful for determining, determining connectivity, including functional groups. And it's generally plotted as frequency versus absorption energy and standardized using chemical shift, measured in parts per million. That's important, ppm, right here, ppm, spectrophotometer frequency. So the results don't depend on the strength of whatever specific spectrometer you're using. The whole scale will be calibrated against a TMS, which is basically an arbitrary thing. Like you need something relative to be compared to. And so TMS is defined as 0 ppm. And so everything else is kind of defined relative to that point. Like it's basically like a ruler. Here's ppm on an x-axis. And so it's like a ruler kind of thing. And this first part of the ruler is 0 ppm, which is also known as the TMS. Okay, and so integration is the area under the peak, under each peak, is proportional to the number of protons producing that peak. So it tells you the relative proton counts across that molecule. So that would be integration. And then deshielding. So deshielding, this is where deshielding happens when you have electron withdrawing groups and they pull electron density away from the proton's nucleus, which lets the proton feel the external magnetic field more directly and more strongly. So by deshielding, it pushes a peak downfield to the left on the spectrum. The opposite would be shielding. So you have shielding and you have deshielding that can occur, right? So deshielding moves the peak further downfield, whereas shielding, you can imagine opposite. So you move to the right, so it'd be upfield. So right versus left. Okay. And that's what we're talking about here, downfield versus upfield. And then now we can go into, let's go into the chart then, because that would help understand like left and right. But it's pretty common sense to understand that downfield versus upfield, but yeah. So that's why scanning this chart from left to right, carboxylic acid and aldehyde protons sitting right next to a strongly electron withdrawing carbonyl show up way downfield. While the protons far from electronegative influence, like those on a simple alkyl chain, cluster more towards the TMS, right? All right, so that's what's happening there. Now for spin-spin coupling. Spin-spin coupling is when hydrogens sit on adjacent atoms, and they interfere with each other's local magnetic environment, splitting each other's peaks, and not sitting each other's. It says splitting here, splitting each other's peaks. So that's spin-spin coupling. So a proton peak splits into n+1 subpeaks, where n is the number of protons 3 bonds away from it, and that gives you the familiar doublets, triplets, and multiplets. So an analogy is this, that you can think of each neighboring proton as a coin flip, heads or tails, spins up or does it spin down, and your proton of interest feels the combined magnetic effect of all its neighbors. So the coin flips all at once, and with one neighbor, there are 2 possible combined outcomes, splitting your peak into a doublet. But with 2 neighbors, there are 3 possible combined outcomes. So you have that one, so you have that one, and then you have its neighbors, right? So then you'd have 3 combined outcomes that are possible, and that gives you a triplet. So that's the n+1 rule. That's why it says, n+1 subpeaks here. That's the n+1 plus 1 role. Okay, so I think that was it. The last one is mass spectroscopy. So mass spectroscopy defines the molecular weight, and it also can help establish structure as well. The molecule collides with an electron, and in the process ejects one of its own electrons, producing a radical cation. So remember, if you release an electron, what are you becoming? You're becoming less negative, in other words, more positive. So you're becoming a radical cation. So the base peak is simply the tallest peak on the spectrum. So tallest peak. Where is the tallest peak? Tallest peak. That's your base peak. And so it's the most abundant fragment, and it isn't necessarily the intact molecule. It's whichever fragment happens to form the most stable cation. Most stable cation. So the fragmentation tends to favor breaking toward more substituted, more stabilized carbocations. The molecular ion peak, right, by contrast, is a peak that represents the actual molecule. So it represents the whole unfragmented molecule, whereas the base peak is kind of fragments. Okay, now we can go into M+1 peak. Why am I covering it there? M+1 peak and M+2 peak. So the M+1 peak comes from the natural relative abundance of the C13 isotope. So because it's basically you're doing it in comparison, which is about 1.1% of all carbon atoms. So out of all the carbon atoms you'll ever find on Earth, you'll have 1.1% of the isotopes of carbon to be C13. So if the more carbons a molecule has, the more of those slightly heavier like lottery tickets it's holding, and the taller that M+1 peak grows. So if M+1 peak's relative height is 4.4%, dividing that by 1.1% tells you that there's 4 carbons in the molecule, for example. So this was an example here. So the M+2 peak flags is a little bit different. Like what it shows is that the presence of a heavier halogen isotope, so Br81 or Cl37, bromine shows up in roughly a 1-to-1 ratio between M and M+2, while chlorine shows up in roughly a 3-to-1 ratio. So basically, you can see in the picture that 1-to-1 pattern directly in bromoethane spectrum. The molecular ion peak and the M+2 come out at exactly equal height. And so remember that converting a carboxylic acid into an acid chloride or an acid bromide back into the carboxylic acids. If you remember that process, this M+2 pattern is exactly how you'd spot that Cl or Br sitting in the mass spectrum. So a roughly equal height or an echo peak for bromine, or a much smaller 1/3 height echo for chlorine, is the instrument's way of telling you that an halogen is present. So this is a mass spectrometry of bromoethane. M+ has similar intensity as M+2. So I just wanted to go over a little bit more for anyone that finds it still confusing, because I know numbers, not everyone is like kind of just a straight numbers person. So like look at the chart, right? You have two axes. You have the y-axis and the x-axis. And the first thing you need to do when learning new charts is understanding what those axes are actually labeling. So the x-axis is basically how heavy is the fragment, how heavy, right? And then so it's mass divided by charge, and since almost everything here carries a charge of +1, you can read it as the mass of whatever piece of the molecule made it to the detector. And then the y-axis is the relative abundance, right? So that's the whole point of us doing this part. And how, in other words, how common was that fragment? And so it's scaled to the tallest peak set at 100%. So at the tallest would be 100% abundance. We're talking about these isotopes, right? Like versions of carbon that can occur, right? And so the tallest spike hitting 100% is your base peak. Okay, so we went over that, base peak. And then, so this is a fragment, not the whole molecule, it's just a fragment under electron impact. And so the neighboring peak right next to it is a related fragment that lost a bit more mass at 29%, which I think is around here, 29%. So at 29%, something that lost more mass. And the tallest peak doesn't have to be the intact molecule. It's just whatever fragment happened to be the most abundant. So that's what we were highlighting earlier. And then the small twin peaks around 79 to 81%, which is around here. It's like around 75. It looks like around 75% actually. That's what's left when the molecule instead loses, its ethyl group and keeps the bromine on its own. So notice there's two close together, roughly similar height. That's bromine's two natural isotopes happening. So that's Br like 79, for example, Br81 showing up here, right? So the pairs of peaks on that are both sitting at, I don't know. Like that's kind of an idea of how you would kind of read the mass spectrometry, in other words. But this was just like an example. Going through actual practice problems will help a lot, and seeing where you are right or wrong about reading them and stuff like that will help. Okay, and last but not least, we're on chapter 12 on separations and purifications, which is pretty interesting. I wasn't never really interested about separation and purifications, but you might be. So anyway, let's start first with extraction. So these are soluble base methods. So you can do extraction, wash, filtration, or recrystallization. For extraction is when you combine two immiscible liquids, in other words, liquids that don't really mix with each other, where one of them easily dissolves your compound of interest. So the nonpolar organic layer dissolves nonpolar compounds. The polar aqueous layer dissolves compounds that are polar. Right? So nonpolar, polar. And so the wash is where you just have the extraction, but it's the reverse of it. So instead of pulling your product out into a new solvent, you run a small amount of solvent over your product to dissolve away impurities instead of leaving the compound of interest behind. So that's the wash. And then for filtration, there's gravity filtration, vacuum filtration. So in filtration, you're basically isolating a solid from the liquid. So the solid is known as the residue, and the liquid is known as filtrate. And so you can use gravity filtration when your product of interest is dissolved into filtrate and you're filtering out the solid in purifications and keeping the liquid. So you can think of this as like a coffee cup and filtering coffee, like beans and stuff. And then vacuum filtration is when your product of interest is the solid itself, and a vacuum pulls the solvent through the filter paper quickly, isolating your solid product on that filter. So seeing pictures and animations might help for filtration, for gravity filtration and vacuum filtration. And then for recrystallization, it's about dissolving your product in the minimum amount of hot solvent possible, right? And then so you're using the minimum amount, and as the solution cools, if the impurities are more soluble than your product, then they will form pure crystals will form pure crystals, and only molecules that match the product's exact shape and packing get invited into that orderly lattice. So crystal lattice structure, right? And the odd-shaped impurity molecules don't fit that pattern, so they end up getting left behind in the liquid, and you filter them away from your now purified crystals, basically. So remember your crystal lattice. Here's your crystal lattice structure. This is a good picture, and then whatever doesn't fit the structure will get filtered away, basically. All right, and then chromatography we went over in biochemistry. So in the biochemistry videos, so I recommend watching that. We went over that in depth. But basically, chromatography is a way to separate two or more molecules from a mixture based on their differing affinities for a stationary phase versus a mobile phase. And I explained this in detail for the biochem video. So an analogy for chromatography is you can picture a race where every runner moves at the same starting speed, but the racetrack itself has different amounts of stickiness for different runners. So some runners get slowed down by the track's texture than others. So molecules that end up so molecules are kind of like the runners, right? So some of them can interact more strongly with the stationary phase, which can lag them behind, but other molecules can interact weakly, and so they run faster with the mobile phase, and that difference in speed is then shown on the chromatography results. Okay, for distillation, and then if you're still confused, my biochem video already goes through chromatography, and you can also look at the appendix for chromatography, which is about appendix on lab techniques, is what it's called, lab techniques. Okay, and then lastly for distillation, distillation is when you're separating liquids based on difference in boiling points. So the liquid with the lowest boiling point will end up vaporizing first, in other words, like shooting up into air as steam. Not with this image, but yeah, shooting up in air as like steam, and once it's condensed back into liquid form, it's collected as distillate. That's what it's called. And so simple distillation works when boiling points are under 150 degrees Celsius and are at least 25 degrees apart from each other. And so that's a wide enough gap that one component just readily vaporizes well before the other, so you're able to basically separate them liquids. Right? And so vacuum distillation should be used when boiling points are over 150 degrees and to avoid degrading a heat-sensitive product. So then applying a vacuum lowers the air pressure above the liquid, which lowers the temperature the liquid needs to reach in order to boil. So that's your vacuum distillation. For fractional distillation, you should use it when boiling points are less than 25 degrees apart, because it allows a more refined separation of liquids by boiling point. Yeah, I don't know if there's anything else I had to say about fractional distillation. It just should be used when the boiling points are less than 25 degrees apart. And since it allows more refined separation, than just simple distillation can manage, right? So an analogy could be like a simple distillation is like one big jump from liquid to vapor to collected distillate. And a fractional distillation column breaks the same idea or the trip into many different hops instead. So many different stages instead. And vapor rises partially, condenses then, and then re-vaporizes repeatedly as it climbs up a column. And each of these little kind of levels or hops nudges that mixture a bit further toward pure separation of the two liquids. Yeah, so if you put enough of those individual stages with each other, even with very close boiling points, they end up evenly separated by the top of the column. So here is, yeah. So this is a nice image for the chapter, and then yeah. So those are some techniques for separation, and that's about it for organic chemistry. And thanks for watching.